From the crushing depths of black holes to the ethereal dance of cosmic phenomena, our reality is far stranger than fiction. Join us as we explore the birth of galaxies, the intricate web of cosmic structure, and the tantalizing possibility of life beyond Earth. The Big Bang Theory is our current best explanation for how the universe began. It proposes that the cosmos started as an incredibly hot, dense point about 13.8 billion years ago. From this initial state, the universe rapidly expanded and cooled, setting the stage for the formation of all matter and energy we observe today. This theory suggests that space itself began expanding, carrying matter and energy along with it. In the first fractions of a second after the Big Bang, the universe underwent a period of exponential growth called inflation. This expansion helped smooth out the distribution of matter and energy, explaining the overall uniformity we see in the cosmos on large scales. As the universe continued to expand and cool, it allowed for the formation of fundamental particles, then atoms, and eventually the first stars and galaxies. The Big Bang Theory is supported by several key pieces of evidence, including the cosmic microwave background radiation, the abundance of light elements in the universe, and the observed expansion of space. While the Big Bang Theory explains many aspects of our universe, it doesn't address what came before or what caused the initial expansion. Scientists continue to research these questions, pushing our understanding of the cosmos even further. The universe is approximately 13.8 billion years old. Scientists have determined this age through a combination of sophisticated observations and complex calculations. One key method involves studying the cosmic microwave background radiation, a faint glow left over from the early universe. By analyzing the patterns in this radiation, scientists can deduce how long ago the universe began. Another approach uses measurements of the expansion rate of the universe. By observing distant galaxies and calculating how quickly they are moving away from us, researchers can work backwards to determine when the expansion began. Scientists also estimate the age of the oldest stars in our galaxy. These ancient stars serve as cosmic timekeepers, providing a minimum age for the universe. By combining these different lines of evidence, researchers have converged on the current estimate of 13.8 billion years, with an uncertainty of only about 100 million years. The Big Bang Theory, our current best explanation for the origin of the universe, is supported by several key pieces of evidence. One of the most compelling is the cosmic microwave background radiation, a faint glow of light that fills the entire sky. This radiation is the afterglow of the Big Bang itself, released when the universe was just 380,000 years old. Its discovery in 1965 provided strong support for the idea that the universe had a hot, dense beginning. Another crucial piece of evidence is the abundance of light elements in the universe. The Big Bang Theory predicts that the early universe was hot enough to forge hydrogen and helium, but not heavier elements. Observations of the cosmos show that roughly 75% of all normal matter is hydrogen, with most of the remainder being helium. This matches precisely what the Big Bang Theory predicts. The expansion of the universe also supports the Big Bang Theory. Observations of distant galaxies show that they are moving away from us, and the farther away they are, the faster they're receding. This suggests that the universe is expanding in all directions, consistent with an explosive beginning from a single point. Lastly, the theory explains the large-scale structure of the universe. Computer simulations based on the Big Bang model accurately predict the observed distribution of galaxies and galaxy clusters. This web-like structure, often called the cosmic web, is a natural consequence of tiny fluctuations in the early universe growing over billions of years under the influence of gravity, just as the Big Bang Theory suggests. Cosmic inflation is a crucial concept in our understanding of the early universe. It describes an incredibly rapid expansion that occurred in the first fraction of a second after the Big Bang. During this brief period, the universe expanded faster than the speed of light, growing from smaller than an atom to about the size of a grapefruit in an unimaginably short time. This rapid expansion helps explain several puzzling features of our universe. It accounts for why the cosmos appears so uniform on large scales, with similar temperatures and densities in all directions. Inflation also explains why the universe is so flat, meaning that parallel lines stay parallel even over vast distances. One of the most intriguing aspects of cosmic inflation is its connection to quantum fluctuations. These tiny ripples in the fabric of space-time, present during inflation, were stretched to cosmic scales. They eventually became the seeds for the formation of galaxies and large-scale structures we see today. Cosmic inflation remains a cornerstone of modern cosmology, providing a framework for understanding the earliest moments of our universe and setting the stage for its subsequent evolution. It connects the quantum world with the large-scale structure of the cosmos, bridging the gap between the infinitesimally small and the unimaginably large. The first few minutes after the Big Bang are known as the primordial nucleosynthesis. This crucial period saw the universe transform from an incredibly hot, dense state into a rapidly expanding cosmic soup of fundamental particles. In the opening seconds, the universe was filled with an unimaginably hot quark-gluon plasma. As it cooled, quarks combined to form protons and neutrons. Within the first 3 minutes, these protons and neutrons began fusing to create the simplest atomic nuclei: hydrogen, helium, and trace amounts of lithium. During this time, the universe was opaque, filled with a fog of electrons that scattered light in all directions. The temperature dropped from billions of degrees to about 1 billion degrees Celsius. This cooling allowed the first atomic nuclei to form, but it was still far too hot for complete atoms to exist. The primordial nucleosynthesis set the stage for the later formation of stars and galaxies. It established the initial ratio of elements that would influence the entire future evolution of the cosmos, making it a cornerstone event in the history of our universe. In the moments after the Big Bang, the universe was an incredibly hot, dense soup of particles. As it expanded and cooled, the first elements began to take shape. This process, known as Big Bang nucleosynthesis, occurred within the first few minutes of the universe's existence. Initially, the universe was filled with hydrogen, the simplest element, consisting of a single proton. As temperatures dropped, some of these protons combined with neutrons to form deuterium, an isotope of hydrogen. Deuterium then fused to create helium, the second lightest element. This primordial nucleosynthesis produced mostly hydrogen and helium, with trace amounts of lithium. These elements formed the building blocks for everything that followed. It would take millions of years and the birth of the first stars for heavier elements to emerge. The creation of these first elements set the stage for the cosmic evolution that followed, leading to the diverse and complex universe we observe today. This early process laid the foundation for all the matter that would eventually form stars, planets, and even life itself. The cosmic microwave background radiation is the oldest light in the universe, a faint glow that fills all of space. This ancient radiation was created about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely for the first time. This primordial light is crucial to our understanding of the early universe. It provides a snapshot of the cosmos when it was just a fraction of its current age, allowing scientists to study the conditions present in those early moments. The cosmic microwave background is remarkably uniform, but it contains tiny fluctuations that reveal the seeds of cosmic structure. By studying these minute variations, astronomers have gained insights into the composition and evolution of the universe. The cosmic microwave background has helped confirm the Big Bang theory and provides evidence for the existence of dark matter and dark energy. It has also allowed scientists to estimate the age and shape of the universe with unprecedented accuracy. Furthermore, this ancient radiation serves as a backlight for the entire observable universe. As it travels through space, it interacts with galaxies and gas clouds, allowing astronomers to detect and study these structures even when they are too faint to observe directly. The cosmic microwave background truly is a cornerstone of modern cosmology, providing a wealth of information about our cosmic origins and evolution. Our understanding of the universe's origins has undergone a remarkable transformation throughout history. Ancient civilizations often attributed cosmic creation to divine beings or mythological events. These early explanations were rooted in cultural beliefs rather than scientific observation. The scientific revolution in the 16th and 17th centuries marked a significant shift in our approach to understanding the cosmos. Astronomers like Copernicus and Galileo challenged the Earth-centered model of the universe, paving the way for a more evidence-based understanding of our place in space. The 20th century brought unprecedented advancements in our knowledge of the universe's beginnings. Einstein's theory of general relativity provided a framework for understanding the fabric of space-time, while Edwin Hubble's observations revealed an expanding universe. These discoveries led to the development of the Big Bang theory, proposed by Georges Lemaitre, which suggests the universe began as an incredibly hot, dense state and has been expanding ever since. Modern cosmology continues to refine our understanding of cosmic origins. Observations of the cosmic microwave background radiation, the discovery of dark matter and dark energy, and advancements in particle physics have all contributed to a more comprehensive picture of the early universe. Today, scientists are exploring concepts like cosmic inflation and the multiverse, pushing the boundaries of our knowledge even further. While the Big Bang theory remains the most widely accepted explanation for the origin of our universe, several alternative theories have been proposed by scientists over the years. One such theory is the steady-state model, which suggests that the universe has always existed and continues to expand, with new matter constantly being created to maintain a constant density. This theory, however, fails to explain the observed cosmic microwave background radiation and the abundance of light elements in the universe, both of which are well accounted for by the Big Bang theory. Another alternative is the cyclic model, which proposes that the universe goes through endless cycles of expansion and contraction. In this view, the Big Bang is just one of many cosmic events in an eternal series. While intriguing, this theory faces challenges in explaining how the universe could survive multiple cycles without succumbing to entropy. The plasma cosmology theory suggests that electromagnetic forces, rather than gravity, are the primary drivers of cosmic structure formation. This idea, however, struggles to explain the large-scale structure of the universe and the cosmic microwave background radiation that the Big Bang theory successfully addresses. These alternative theories are less widely accepted because they often lack the observational evidence and explanatory power of the Big Bang theory. The Big Bang model has successfully predicted and explained numerous cosmic phenomena, making it the most robust and well-supported explanation for the origin and evolution of our universe currently available to science. We know the universe is expanding through several key observations. The most significant evidence comes from the redshift of distant galaxies. As galaxies move away from us, the light they emit stretches, shifting towards the red end of the spectrum. This phenomenon, first observed by Edwin Hubble in the 1920s, revealed that the farther a galaxy is from us, the faster it appears to be moving away. Further evidence comes from the cosmic microwave background radiation, a faint glow left over from the early universe. This radiation's properties align perfectly with predictions of an expanding universe model. Additionally, the abundance of light elements in the cosmos, such as hydrogen and helium, matches what we'd expect if the universe began in a hot, dense state and has been expanding ever since. The implications of an expanding universe are profound. It suggests that the universe had a beginning, supporting the Big Bang theory. This expansion also affects the ultimate fate of the universe. If the expansion continues to accelerate, as current observations indicate, the universe may end in a big freeze, where all matter is spread so thin that no new stars can form. The expanding universe also challenges our understanding of physics. It implies the existence of dark energy, a mysterious force counteracting gravity on cosmic scales. This discovery has opened up new areas of research and forced us to reconsider our models of the fundamental nature of space, time, and matter. Galaxies are vast cosmic cities, home to billions of stars, planets, gas, dust, and mysterious dark matter. These colossal structures serve as the building blocks of our universe, each one a unique collection of celestial objects bound together by gravity. The Milky Way, our cosmic address, is just one of countless galaxies scattered across the cosmos. The formation of galaxies is a complex process that began in the early universe. It all started with tiny fluctuations in the distribution of matter after the Big Bang. Over time, gravity caused these small irregularities to grow, drawing in more and more material. As these regions became denser, they began to collapse under their own weight, forming the seeds of future galaxies. As these proto-galaxies grew, they continued to attract more matter, including the elusive dark matter. This invisible substance played a crucial role, providing additional gravitational pull to hold these emerging structures together. Meanwhile, ordinary matter began to cool and condense, eventually forming the first stars and setting the stage for the complex galaxies we see today. Galaxies continue to evolve long after their initial formation. They can grow through mergers with other galaxies, a cosmic dance that can take billions of years to complete. This ongoing process of galactic evolution shapes the diverse array of galaxy types we observe in the universe, from majestic spirals to massive ellipticals, each with its own unique history and characteristics. The number of galaxies in the observable universe is truly staggering. Current estimates suggest there are approximately 2 trillion galaxies spread across the vast expanse of space we can see. This figure is based on deep-field observations made by advanced telescopes like the Hubble Space Telescope and sophisticated computer simulations. To put this enormous number into perspective, if you were to count one galaxy per second without stopping, it would take you over 63,000 years to count them all. And this is just within the observable universe, the portion of the cosmos that light has had time to reach us from since the Big Bang. These galaxies come in a variety of shapes and sizes, from massive elliptical galaxies containing trillions of stars to smaller, irregular dwarf galaxies. Our own Milky Way is just one among these countless stellar cities, each harboring its own unique collection of stars, planets, and cosmic wonders. It is important to note that as our technology and understanding improve, this estimate may change. Future telescopes and observations might reveal even more galaxies, further expanding our cosmic census and deepening our appreciation for the immensity of the universe. Galaxies come in a variety of shapes and sizes, each with its own unique characteristics. The 3 main types of galaxies are spiral, elliptical, and irregular. Spiral galaxies, like our own Milky Way, are characterized by their distinctive spiral arms that wind outward from a central bulge. These arms are filled with gas, dust, and younger stars, giving them a bluish appearance. The central bulge contains older, redder stars and often houses a supermassive black hole. Spiral galaxies are known for their active star formation and can be further classified based on the tightness of their spiral arms and the size of their central bulge. Elliptical galaxies, in contrast, lack the spiral structure and appear as smooth, featureless ovals of varying elongation. These galaxies are predominantly composed of older, redder stars and contain little gas or dust. As a result, they have minimal ongoing star formation. Elliptical galaxies range in size from dwarf ellipticals to giant ellipticals, which can be hundreds of times more massive than the Milky Way. Irregular galaxies are the cosmic oddballs, lacking the symmetry and defined structure of spirals or ellipticals. These galaxies often have chaotic appearances, possibly due to gravitational interactions with other galaxies or intense bursts of star formation. Irregular galaxies tend to be smaller and are often rich in gas and dust, making them hotbeds of star formation activity. The Milky Way is our home galaxy, a vast collection of stars, planets, gas, dust, and dark matter bound together by gravity. It contains an estimated 200 billion to 400 billion stars, with our Sun being just one of them. The Milky Way stretches across approximately 100,000 light-years in diameter, forming a disc-like structure with spiral arms extending outward from a central bulge. Our galaxy is classified as a barred spiral galaxy. This means it has a distinct spiral shape with arms that wind outward from its center, creating a cosmic pinwheel appearance. The barred part of its classification refers to a bar-shaped structure of stars that runs through the galaxy's core, connecting the inner ends of the spiral arms. The Milky Way's spiral arms are where most of its star formation occurs. These arms contain abundant gas and dust, providing the raw materials for new stars to be born. Our solar system is located in one of these arms, known as the Orion Arm, roughly 26,000 light-years from the galactic center. At the heart of our galaxy lies a supermassive black hole called Sagittarius A star. This cosmic giant has a mass equivalent to about 4 million suns and plays a crucial role in shaping the Milky Way's structure and evolution. Despite its enormous size and influence, our galaxy continues to grow and change, interacting with nearby galaxies and constantly forming new stars. Scientists employ a variety of sophisticated techniques to study the formation and evolution of galaxies. One key method involves observing galaxies at different distances from Earth, which effectively allows astronomers to look back in time. Light from more distant galaxies takes longer to reach us, revealing how galaxies appeared billions of years ago. Powerful telescopes, both on Earth and in space, capture detailed images and spectra of galaxies. These observations provide crucial data about galactic structure, composition, and behavior. The Hubble Space Telescope, for instance, has been instrumental in revealing the diversity of galactic shapes and sizes across cosmic history. Computer simulations play a vital role in understanding galaxy formation. Scientists use supercomputers to model the complex interactions of dark matter, gas, and stars over billions of years. These simulations help test theories about how galaxies grow and change over time, allowing researchers to compare their models with real observations. Another important approach is studying the chemical composition of stars within galaxies. As older stars die and new ones form, the mix of elements in a galaxy changes. By analyzing this chemical evolution, scientists can piece together the history of star formation and galactic development. This cosmic detective work continues to deepen our understanding of how the magnificent structures we see in the night sky came to be. Dark matter and dark energy, though invisible and mysterious, play crucial roles in shaping the universe we see today. Dark matter, which makes up about 27% of the cosmos, acts as a gravitational scaffold for galaxy formation. Its immense gravitational pull draws in normal matter, creating dense regions where stars and galaxies can form. Without dark matter, the universe would likely be a vast, diffuse cloud of gas, unable to coalesce into the intricate structures we observe. Dark energy, on the other hand, accounts for roughly 68% of the universe and has a very different effect. It acts as a repulsive force, causing the expansion of the universe to accelerate. This expansion influences how galaxies form and evolve over cosmic time. In the early universe, dark energy played a minimal role, allowing gravity to pull matter together. But as the universe aged, dark energy became more dominant, eventually overpowering gravity on the largest scales. The interplay between dark matter and dark energy creates a delicate balance in galaxy formation. Dark matter provides the initial gravitational wells for galaxies to form, while dark energy determines the rate at which the universe expands, affecting how much matter can be drawn into these wells. This balance has led to the diverse array of galaxies we see today, from small, dense dwarf galaxies to massive spiral and elliptical galaxies. Understanding dark matter and dark energy is crucial for explaining not just how individual galaxies form, but also how they cluster together in vast cosmic webs. These invisible components shape the large-scale structure of the universe, guiding the formation of galaxy clusters and the immense voids between them. As we continue to study these enigmatic forces, we gain deeper insights into the fundamental nature of our cosmos and its evolution. Galactic collisions occur when two or more galaxies come close enough for their gravitational forces to interact strongly. These cosmic encounters can range from near misses to direct impacts, each leaving a lasting imprint on the involved galaxies. As massive structures containing billions of stars, gas, and dust, colliding galaxies undergo dramatic transformations that shape their future evolution. During a collision, the immense gravitational forces at play cause stars and gas to be flung into new orbits. This process can create long tidal tails stretching out from the galaxies, forming bridges of stars and gas between them. The collision also triggers intense bursts of star formation as gas clouds are compressed, leading to the birth of millions of new stars in a relatively short cosmic timespan. Interestingly, despite the enormous scale of these events, individual stars rarely collide due to the vast distances between them. Instead, the primary impact is on the overall structure and composition of the galaxies. Spiral galaxies, for instance, can lose their distinctive disk shape and transform into elliptical galaxies through repeated collisions and mergers. Galactic collisions play a crucial role in galaxy evolution by mixing stellar populations, altering galactic morphology, and influencing star formation rates. They can lead to the growth of supermassive black holes at galactic centers and contribute to the formation of larger cosmic structures. Our own Milky Way galaxy bears evidence of past collisions and is on a collision course with the neighboring Andromeda galaxy, set to occur in about 4 billion years. The local group is a collection of galaxies bound together by gravity, forming our cosmic neighborhood in the vast expanse of the universe. This cluster spans about 10 million light-years in diameter and contains more than 50 galaxies of various sizes and types. At the heart of the local group are its largest members, the Andromeda galaxy and our own Milky Way. These two spiral galaxies dominate the group, each hosting hundreds of billions of stars. The third largest galaxy in the local group is Triangulum, another spiral galaxy, though significantly smaller than its two giant neighbors. Orbiting these main galaxies are numerous dwarf galaxies. The Milky Way is accompanied by the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere. Other notable dwarf galaxies include Sagittarius, Ursa Minor, and Draco. Andromeda has its own retinue of smaller companions, including M32 and M110. The local group also contains several isolated dwarf galaxies, not clearly associated with either of the major spirals. These include galaxies like NGC 6822 and IC 1613. Together, this assortment of galaxies forms a gravitationally bound family, moving through the cosmos as a unit and shaping each other's evolution over billions of years. Supermassive black holes play a crucial role in the formation and growth of galaxies. These cosmic giants, with masses millions or billions of times that of our Sun, reside at the hearts of most large galaxies, including our own Milky Way. Their immense gravitational pull influences the movement and distribution of stars, gas, and dust within their host galaxies. As galaxies form and evolve, supermassive black holes grow alongside them in a symbiotic relationship. They feed on the surrounding matter, drawing in gas and stars from their vicinity. This process releases enormous amounts of energy, creating what we call active galactic nuclei. These energetic cores can produce powerful jets and outflows that extend far beyond the galaxy itself, shaping the intergalactic medium. The energy released by an active supermassive black hole can have profound effects on its host galaxy. It can heat up and expel gas, potentially halting star formation in a process called quenching. This feedback mechanism is thought to be responsible for regulating the growth of galaxies, preventing them from becoming too large. Without this control, galaxies might continue to form stars indefinitely, growing to sizes we do not observe in our universe. Recent observations have revealed that the mass of a supermassive black hole is closely correlated with the properties of its host galaxy, such as the velocity dispersion of stars in the galactic bulge. This relationship, known as the black hole galaxy connection, suggests a deep link between the growth of these cosmic behemoths and the evolution of their galactic homes. Understanding this connection is a key area of research in modern astrophysics, as it holds clues to the cosmic history of galaxy formation and the role of supermassive black holes in shaping our universe. The cosmic web is the largest known structure in the universe, a vast network of interconnected filaments and voids that stretches across the cosmos. This intricate pattern formed in the early stages of the universe as gravity pulled matter together into dense regions while leaving other areas nearly empty. The result is a complex, three-dimensional tapestry that resembles a giant spiderweb on cosmic scales. Galaxies are the building blocks of this cosmic web, clustered along its filaments like glittering jewels. These filaments are made up of dark matter and gas, acting as cosmic highways that guide the formation and movement of galaxies. At the intersections of these filaments, we find massive galaxy clusters, the largest gravitationally bound structures in the universe. Between the filaments lie vast cosmic voids, enormous regions of space nearly devoid of galaxies. These voids can span hundreds of millions of light-years across, dwarfing even the largest galaxy clusters. The contrast between the densely populated filaments and the empty voids creates the distinctive web-like appearance that gives this structure its name. The cosmic web plays a crucial role in the evolution of galaxies. As galaxies travel along the filaments, they interact with one another, merging and growing over billions of years. This process shapes the diverse array of galaxies we observe today, from small dwarf galaxies to massive elliptical galaxies at the hearts of galaxy clusters. Stars form within vast clouds of gas and dust, known as molecular clouds. These cosmic nurseries contain primarily hydrogen with traces of helium and other elements. The process begins when a portion of the cloud becomes denser than its surroundings, often triggered by external forces like shock waves from nearby supernovas or collisions between clouds. As gravity takes hold, the dense region starts to collapse under its own weight. This collapse causes the cloud to fragment into smaller clumps, each potentially becoming a star. As a clump continues to contract, its core becomes increasingly hot and dense. The gravitational energy of the collapsing material is converted into heat, raising the temperature at the center. When the core temperature reaches about 10 million degrees Celsius, nuclear fusion ignites. Hydrogen atoms begin to fuse into helium, releasing enormous amounts of energy. This marks the birth of a star, as the outward pressure from fusion reactions balances the inward pull of gravity, stabilizing the newborn star. The conditions necessary for star formation include sufficiently cool and dense gas, usually found in the spiral arms of galaxies or in irregular galaxies. The presence of heavy elements formed in previous generations of stars also plays a crucial role in cooling the gas and allowing it to collapse. Without these elements, the early universe could not form stars as efficiently as we observe today. The main sequence is the primary stage of stellar evolution, where stars spend most of their existence. During this phase, stars maintain a delicate balance between the outward pressure of nuclear fusion and the inward pull of gravity. This equilibrium allows stars to shine steadily for millions or billions of years, depending on their mass. Stars on the main sequence fuse hydrogen into helium in their cores through nuclear fusion. This process generates an enormous amount of energy, which we observe as starlight. The stability of main sequence stars comes from the consistent rate of fusion, which produces just enough outward pressure to counteract the star's own gravity trying to collapse it. The reason most stars spend the majority of their lives on the main sequence is simple. Hydrogen is the most abundant element in the universe, and stars have a lot of it. A star like our Sun will spend about 10 billion years on the main sequence, slowly converting its hydrogen fuel into helium. Larger stars burn through their fuel more quickly, while smaller stars can remain on the main sequence for much longer. Only when a star exhausts the hydrogen in its core does it leave the main sequence, entering the later stages of its life cycle. This transition marks the beginning of more dramatic changes in the star's structure and appearance, ultimately leading to its final fate as a white dwarf, neutron star, or black hole. Stars generate their immense energy through a process called nuclear fusion. Deep within the core of a star, where temperatures soar to millions of degrees, hydrogen atoms are forced together under extreme pressure. These conditions are so intense that the hydrogen nuclei overcome their natural repulsion and fuse to form helium. This fusion releases an enormous amount of energy in the form of light and heat. The specific type of fusion occurring in most stars is known as the proton-proton chain reaction. In this process, 4 hydrogen nuclei combine to create one helium nucleus. The mass of the resulting helium is slightly less than the original hydrogen. This tiny difference in mass is converted directly into energy, following Einstein's famous equation that relates mass to energy. For stars like our Sun, this fusion process has been ongoing for billions of years and will continue for billions more. The energy produced in the core gradually makes its way to the surface, where it radiates into space as the light and heat we observe. This constant outpouring of energy is what keeps stars shining brightly across the cosmos. The fusion process in stars is not only the source of their brilliance, but also the origin of many elements in the universe. As stars age and exhaust their hydrogen fuel, they begin fusing heavier elements, creating the building blocks for planets, moons, and even life itself. The color of a star is primarily determined by its surface temperature. This temperature is a result of the star's mass, age, and stage in its life cycle. Stars with higher surface temperatures appear blue or white, while cooler stars appear red or orange. A star's color provides astronomers with valuable information about its characteristics. Blue stars are the hottest, with surface temperatures exceeding 20,000 Kelvin. These massive, bright stars burn through their fuel quickly and have relatively short lifespans. White stars, like our Sun, have intermediate temperatures around 6,000 Kelvin and are considered average in terms of mass and lifespan. Yellow and orange stars are cooler, with temperatures ranging from 4,000 to 5,000 Kelvin. These stars are often smaller and less massive than our Sun, and they can live for billions of years. Red stars are the coolest, with surface temperatures below 4,000 Kelvin. These can be either small, low-mass stars that burn their fuel slowly, or giant stars nearing the end of their lives. By observing a star's color, scientists can estimate its temperature, mass, and age. This information helps astronomers understand stellar evolution, classify stars, and study the composition and history of galaxies. The color of stars also plays a crucial role in determining the potential habitability of planets orbiting them, as it influences the amount and type of radiation reaching those worlds. Stars die in different ways depending on their mass and composition. For lower mass stars like our Sun, the process is relatively gentle. As they exhaust their hydrogen fuel, they expand into red giants, shedding their outer layers to form beautiful planetary nebulae. The exposed core becomes a white dwarf, slowly cooling over billions of years. More massive stars face a more dramatic end. When they run out of fuel, they collapse under their own gravity. This triggers a powerful explosion called a supernova, which can briefly outshine entire galaxies. The fate of the stellar remnant depends on the original star's mass. Stars up to about 20 times the mass of our Sun leave behind incredibly dense neutron stars. Even more massive stars collapse completely, forming black holes from which not even light can escape. The initial mass of a star is the primary factor determining its fate. However, other influences come into play. Binary star systems, where two stars orbit each other closely, can alter stellar evolution. Mass transfer between the stars or mergers can lead to unusual outcomes. Additionally, a star's metal content, referring to elements heavier than helium, can affect its lifespan and final stages. Regardless of their specific fate, dying stars play a crucial role in cosmic evolution. They spread heavy elements into space, enriching the interstellar medium. This material eventually forms new stars, planets, and even the building blocks of life, connecting the death of stars to the birth of new worlds and potentially life itself. A supernova is the explosive death of a massive star, a cosmic event so powerful it can outshine entire galaxies. This stellar cataclysm occurs when a star at least 8 times more massive than our Sun reaches the end of its life. As the star exhausts its nuclear fuel, it can no longer support itself against the crushing force of gravity. In the final moments, the star's core collapses under its own weight. This collapse triggers a massive explosion that tears the star apart, releasing an enormous amount of energy and scattering its outer layers into space. The intensity of this blast is so great that it can briefly rival the brightness of billions of stars combined. Supernovae play a crucial role in the cosmic ecosystem. They forge and distribute heavy elements throughout the universe, enriching the interstellar medium with materials essential for the formation of new stars, planets, and even life itself. The shock waves from these explosions can also trigger the birth of new stars in nearby gas clouds. Astronomers classify supernovae into different types based on their characteristics, but all share the common thread of being among the most energetic and influential events in the cosmos. These stellar explosions continue to fascinate scientists, offering valuable insights into the life cycles of stars and the evolution of our universe. Neutron stars are incredibly dense stellar remnants that form when massive stars exhaust their nuclear fuel and collapse. These cosmic objects are so compact that a teaspoon of neutron star material would weigh billions of tons on Earth. They typically have a diameter of only about 20 kilometers, but contain more mass than our Sun. The birth of a neutron star begins when a star at least 8 times more massive than our Sun reaches the end of its life. As the star's core runs out of fuel for nuclear fusion, it can no longer support itself against gravity. The outer layers of the star explode in a spectacular supernova, while the core implodes under its own weight. During this implosion, protons and electrons in the core are squeezed together so tightly that they combine to form neutrons, hence the name neutron star. The neutrons resist further compression, halting the collapse and leaving behind an object of unimaginable density. A neutron star's gravity is so strong that light rays are noticeably bent as they pass near its surface. These stellar remnants spin rapidly, sometimes rotating hundreds of times per second. As they spin, they emit beams of electromagnetic radiation from their magnetic poles. If these beams sweep past Earth, we observe the neutron star as a pulsar, detecting regular pulses of radiation like cosmic lighthouses. Pulsars are a fascinating type of neutron star, the remnants of massive stars that have exploded as supernovas. These cosmic objects are incredibly dense, with a mass greater than our Sun, compressed into a sphere only about 20 kilometers across. What sets pulsars apart from other neutron stars is their rapid rotation and powerful magnetic fields, which combine to create a unique phenomenon. As pulsars spin, they emit beams of electromagnetic radiation from their magnetic poles. These beams sweep across space like cosmic lighthouses, and when they pass Earth, we detect regular pulses of radiation. This is why they're called pulsars, short for pulsating stars. The regularity of these pulses is remarkable, with some pulsars rotating hundreds of times per second with clock-like precision. The key difference between pulsars and other neutron stars lies in this observable pulsing behavior. While all neutron stars are extremely dense and have strong magnetic fields, not all of them emit detectable pulses. Some neutron stars rotate too slowly or have misaligned magnetic fields that prevent us from observing the lighthouse effect. Pulsars also tend to be younger and more energetic than other neutron stars. Over time, pulsars slow down and eventually stop emitting detectable pulses, becoming more like typical neutron stars. This makes pulsars invaluable for studying the life cycles of these extreme stellar remnants and the physics of ultra-dense matter. Binary star systems form when two stars are born from the same collapsing cloud of gas and dust. As the cloud fragments and condenses, it can create two separate stellar cores that orbit each other due to their mutual gravitational attraction. This process occurs in about half of all star formations, making binary systems incredibly common throughout the universe. The evolution of binary stars is a complex dance influenced by their masses, separation, and initial orbital characteristics. If the stars are far apart, they may evolve almost independently, each following a path similar to that of a single star. However, when the stars are close together, their evolution becomes intertwined in fascinating ways. As the stars age, the more massive star typically evolves faster, expanding into a red giant. If the stars are close enough, this expansion can lead to mass transfer between the stars. The larger star may lose its outer layers to its companion, dramatically altering the future of both stars. This process can lead to various exotic outcomes, including the formation of white dwarfs, neutron stars, or even black holes. In some cases, the interaction between binary stars can result in explosive events. If one star becomes a white dwarf and continues to accrete matter from its companion, it may eventually trigger a Type 1, a supernova. Alternatively, if both stars are massive enough, they might merge, potentially creating a kilonova or a more powerful supernova. These events play crucial roles in dispersing heavy elements throughout the universe, contributing to the cosmic chemical evolution that ultimately enabled life as we know it. Stars come in an astonishing range of sizes, from cosmic giants to stellar dwarfs. The largest known star is a hypergiant called UY Scuti, located about 10,000 light-years from Earth in the constellation Scutum. This colossal star has a radius estimated to be more than 1,700 times that of our Sun. If placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter, engulfing everything in its path. At the other end of the spectrum, we find the smallest known stars, which are a class of ultra-cool dwarfs called brown dwarfs. These objects blur the line between stars and planets as they lack sufficient mass to sustain hydrogen fusion in their cores. The smallest confirmed brown dwarf is Ogle 2016 BLG 1540L, with a radius just slightly larger than that of Jupiter. Despite its small size, it still has about 80 times the mass of Jupiter due to its much higher density. Between these extremes lies a vast array of stellar objects, each with unique characteristics. Red dwarfs, for instance, are the most common type of star in our galaxy and can be as small as 1/10 the mass of our Sun. Neutron stars, the collapsed cores of once massive stars, are even smaller in size but incredibly dense, packing more mass than our Sun into a sphere only about 20 kilometers across. This incredible diversity in stellar sizes showcases the complexity and wonder of our universe. From the mind-boggling expanse of hypergiants to the diminutive brown dwarfs, each star tells a story of cosmic evolution and the intricate balance of forces that shape our galaxy and beyond. Black holes are among the most enigmatic objects in the universe. They are regions of space where gravity is so intense that nothing, not even light, can escape once it passes the event horizon. This extreme gravitational pull is what gives black holes their name, as they appear completely dark against the backdrop of space. The formation of a black hole typically begins with the death of a massive star. When a star at least 20 times more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against its own gravity. The star's core collapses inward with tremendous force, while its outer layers are violently ejected in a supernova explosion. If the collapsing core is sufficiently massive, no known force can stop its collapse, and it will form a singularity, a point of infinite density and zero volume. Interestingly, not all black holes form from dying stars. Supermassive black holes, which can be millions or even billions of times more massive than our Sun, are found at the centers of most galaxies, including our own Milky Way. The origins of these behemoths are still debated, but they may have formed from the collapse of enormous clouds of gas in the early universe or from the merging of multiple smaller black holes over time. As black holes consume matter from their surroundings, they can grow even larger. Gas, dust, and even entire stars that venture too close are stretched and compressed as they fall into the black hole, a process astronomers call spaghettification. This infalling matter forms a swirling disk around the black hole, heating up to extreme temperatures and often emitting powerful jets of radiation detectable across vast cosmic distances. Black holes come in a range of sizes, each with unique characteristics and origins. Stellar black holes form when massive stars collapse at the end of their lives. These cosmic objects typically have masses between 5 and several dozen times that of our Sun. Despite their relatively small size compared to other types, stellar black holes exert an immense gravitational pull on their surroundings. At the other end of the scale are supermassive black holes. These giants lurk at the centers of most galaxies, including our own Milky Way. With masses ranging from millions to billions of times that of the Sun, supermassive black holes play a crucial role in shaping galactic structure and evolution. Scientists are still working to understand how these behemoths form and grow over cosmic time. Intermediate mass black holes bridge the gap between stellar and supermassive varieties. These elusive objects have masses ranging from about 100 to 1 million times that of the Sun. While their existence has long been theorized, only recently have astronomers begun to find compelling evidence for intermediate mass black holes in certain star clusters and small galaxies. The rarest and most intriguing category is primordial black holes. Unlike their counterparts that form from collapsing stars, these hypothetical objects may have been created in the extreme conditions of the early universe, mere fractions of a second after the Big Bang. If they exist, primordial black holes could range from microscopic sizes to masses comparable to small stars, potentially offering insights into the nature of dark matter and the earliest moments of cosmic history. The event horizon of a black hole marks a critical boundary in space. It is the point of no return, where the gravitational pull becomes so intense that nothing, not even light, can escape. This invisible barrier separates the observable universe from the mysterious interior of the black hole. At the event horizon, the laws of physics as we know them begin to break down. Time and space become warped in extreme ways, leading to effects that challenge our understanding of the universe. For an outside observer, objects approaching the event horizon appear to slow down and freeze in time, never quite crossing the boundary. The size of an event horizon depends on the mass of the black hole. Stellar black holes, formed from collapsed stars, have event horizons that might span just a few kilometers. Supermassive black holes at the centers of galaxies can have event horizons millions or even billions of kilometers across. Studying event horizons provides crucial insights into gravity, space-time, and the nature of our universe. Scientists continue to probe these cosmic boundaries, seeking to unravel the mysteries that lie beyond, where our current theories of physics no longer apply. Black holes may be invisible, but scientists have developed ingenious methods to detect these cosmic enigmas. One key approach involves observing the effects black holes have on their surroundings. As matter falls towards a black hole, it forms a swirling disk of gas and dust called an accretion disk. This material heats up to extreme temperatures, emitting powerful X-rays that can be detected by space-based telescopes. Another telltale sign of a black hole is its gravitational influence on nearby stars. By carefully tracking the motions of stars, astronomers can infer the presence of an unseen massive object tugging on them. This technique led to the discovery of the supermassive black hole at the center of our Milky Way galaxy. Gravitational waves offer a revolutionary new way to detect black holes. When two black holes collide, they send ripples through the fabric of space-time. These waves can be measured by extremely sensitive detectors on Earth, providing direct evidence of black hole mergers. Scientists also look for gravitational lensing, where the immense gravity of a black hole bends light from distant objects behind it. This distortion can create multiple images or rings of light, revealing the presence of an otherwise invisible black hole. These diverse methods allow researchers to study black holes despite their light-absorbing nature. As matter and light draw near a black hole, they enter a realm where the laws of physics are pushed to their limits. The immense gravitational pull of the black hole begins to exert its influence, warping the very fabric of space-time around it. This distortion becomes more pronounced the closer an object gets to the black hole's event horizon, the point of no return. For matter approaching a black hole, the gravitational forces become increasingly intense. Objects are stretched and compressed in a process astronomers call spaghettification. This phenomenon occurs because the gravitational pull on the part of an object closest to the black hole is significantly stronger than on the part farther away, causing it to be stretched like a piece of cosmic spaghetti. Light behaves differently as it nears a black hole. While light typically travels in straight lines, the extreme curvature of space-time around a black hole causes light to follow curved paths. This effect, known as gravitational lensing, can make objects behind the black hole appear distorted or even create multiple images of the same object. At the event horizon, the gravitational pull becomes so strong that even light cannot escape. Beyond this boundary, our current understanding of physics breaks down, and the known laws of nature no longer apply. This makes black holes not only fascinating cosmic objects, but also crucial laboratories for testing our most fundamental theories about the universe. Hawking radiation is a remarkable phenomenon, theorized by the renowned physicist Stephen Hawking. This concept challenges our understanding of black holes and their seemingly inescapable nature. Contrary to the classical view that nothing can escape a black hole, Hawking radiation suggests that black holes actually emit a faint glow of particles over time. This radiation occurs due to quantum effects near the event horizon, the boundary beyond which nothing can escape the black hole's gravitational pull. Quantum fluctuations cause pairs of particles and antiparticles to spontaneously appear and disappear. Normally, these pairs quickly annihilate each other. However, near the event horizon, one particle might fall into the black hole while the other escapes, appearing as radiation emitted from the black hole. The emission of Hawking radiation has profound implications for black holes. As they radiate energy, black holes gradually lose mass. This process is extremely slow for large black holes, but becomes more significant for smaller ones. Over immense periods of time, this radiation could cause a black hole to evaporate completely, challenging the notion that black holes are eternal. Hawking radiation connects the worlds of quantum mechanics and general relativity, two fundamental theories that have long resisted unification. It provides a crucial link between the behavior of the very small and the very large in our universe, offering insights into the nature of gravity, space, and time at their most extreme. Black holes and time dilation share a profound connection rooted in Einstein's theory of general relativity. As we approach a black hole, the intense gravitational field dramatically slows the passage of time relative to distant observers. This effect becomes more pronounced the closer we get to the black hole's event horizon, the boundary beyond which nothing can escape its gravitational pull. Near the event horizon, time practically crawls to a standstill from an outside perspective. An astronaut falling into a black hole would experience time normally, but to a distant observer, the astronaut would appear to move in slow motion, eventually freezing in time at the event horizon. This extreme time dilation is a consequence of the black hole's immense gravitational warping of space-time. Interestingly, this time dilation effect extends beyond black holes. We experience a mild version of it on Earth, where time passes slightly faster at higher altitudes compared to sea level due to our planet's gravity. However, the difference is so minuscule that we do not notice it in everyday life. Black holes simply take this principle to the extreme. The relationship between black holes and time dilation highlights the malleable nature of time itself. It challenges our intuitive understanding of the universe and reveals the profound impact of gravity on the fabric of space-time, showcasing the extraordinary phenomena that occur in the most extreme environments of our cosmos. Supermassive black holes play a crucial role in shaping the evolution of galaxies. These cosmic giants, residing at the hearts of most large galaxies, exert a profound influence on their surroundings through various mechanisms. One of the primary ways supermassive black holes affect galaxy evolution is through their intense gravitational pull. As they attract nearby stars and gas, they create a swirling disk of material around themselves. This process of feeding on surrounding matter can trigger bursts of star formation in the galaxy, influencing its overall structure and composition. Additionally, supermassive black holes can generate powerful jets of energy and particles that extend far beyond the galaxy itself. These jets interact with the surrounding intergalactic medium, heating it up and preventing the infall of cool gas that would otherwise fuel star formation. This process, known as feedback, can effectively regulate the growth of the galaxy, explaining why we observe a correlation between the mass of a supermassive black hole and the mass of its host galaxy. Furthermore, when galaxies merge, their central black holes also combine, releasing enormous amounts of energy in the form of gravitational waves. This cosmic dance of merging black holes can significantly impact the structure and dynamics of the resulting galaxy, shaping its future evolution and characteristics. Quasars are among the brightest and most energetic objects in the universe. These cosmic powerhouses are actually the active cores of distant galaxies, driven by supermassive black holes at their centers. The term quasar is short for quasi-stellar object, as they initially appeared star-like when first observed. At the heart of a quasar lies a supermassive black hole, typically millions or even billions of times more massive than our Sun. As matter falls towards this black hole, it forms a swirling disk of gas and dust called an accretion disk. The intense gravitational forces and friction within this disk heat the material to extremely high temperatures, causing it to emit vast amounts of energy across the electromagnetic spectrum. The most distinctive feature of a quasar is its incredible luminosity. A single quasar can outshine an entire galaxy of hundreds of billions of stars, making it visible from billions of light-years away. This immense energy output is what allows astronomers to detect and study these objects despite their vast distances from Earth. Quasars also produce powerful jets of particles and energy that can extend far beyond their host galaxies. These jets, propelled by the intense magnetic field surrounding the black hole, can influence the evolution of the quasar's host galaxy and even affect the intergalactic medium. The study of quasars provides valuable insights into the formation and growth of galaxies, as well as the behavior of matter under extreme conditions near black holes. Black holes are among the most mysterious objects in the universe, and what happens inside them pushes the boundaries of our understanding of physics. As matter crosses the event horizon, the point of no return, it experiences extreme gravitational forces. These forces stretch and compress incoming material in a process called spaghettification, where objects are elongated into thin strands. Beyond the event horizon, our current models of physics break down. One theory suggests that at the center of a black hole lies a singularity, a point of infinite density where space and time cease to have meaning. However, some scientists argue that quantum effects might prevent the formation of a true singularity, instead creating an extremely dense core of exotic matter. Another intriguing theory proposes that black holes could be gateways to other universes or different regions of our own universe. This concept, known as a white hole, suggests that matter falling into a black hole might emerge elsewhere in space and time. However, there is currently no observational evidence to support this idea. Some researchers speculate that information about everything that falls into a black hole might be preserved on its event horizon, like a hologram. This holographic principle could potentially resolve the black hole information paradox, which arises from the conflict between quantum mechanics and general relativity in describing what happens to information in a black hole. Exoplanets are worlds that orbit stars beyond our solar system. These distant planets come in a variety of sizes and compositions, from gas giants larger than Jupiter to small rocky bodies similar to Earth. The discovery of exoplanets has revolutionized our understanding of planetary systems and the potential for life elsewhere in the universe. Scientists employ several ingenious methods to detect these far-off worlds. One common technique is the transit method, where astronomers measure the slight dimming of a star's light as an exoplanet passes in front of it. This tiny dip in brightness, often less than 1%, can reveal the planet's size and orbit. Another approach is the radial velocity method, which detects the subtle wobble of a star caused by the gravitational pull of an orbiting planet. As the planet tugs on its star, the star's light shifts slightly towards the red or blue end of the spectrum. By measuring these minute color changes, scientists can infer the presence and properties of exoplanets. More advanced techniques include direct imaging, which captures actual pictures of exoplanets by blocking out the intense light of their host stars, and gravitational microlensing, which uses the bending of light by gravity to detect planets around distant stars. These methods have led to the discovery of thousands of exoplanets, expanding our cosmic horizons and fueling the search for potentially habitable worlds beyond Earth. As of today, astronomers have confirmed the existence of over 5,000 exoplanets, with thousands more candidates awaiting verification. This number continues to grow rapidly as our detection methods and technologies improve. The majority of these discoveries have been made in the past 3 decades, marking a revolutionary period in our understanding of planetary systems beyond our own. These exoplanets come in a wide variety of sizes and types, ranging from small, rocky worlds similar to Earth to massive gas giants larger than Jupiter. Some orbit their stars in scorching proximity, while others drift in the freezing outer reaches of their systems. Many of these worlds challenge our preconceptions about planetary formation and evolution. The hunt for exoplanets has revealed that planetary systems are remarkably common in our galaxy. Nearly every star we observe closely seems to host at least one planet, suggesting that there could be billions of planets in the Milky Way alone. This abundance has profound implications for the potential prevalence of life in the universe. As we continue to refine our search techniques and launch more advanced telescopes, we expect the number of known exoplanets to increase dramatically. Each new discovery brings us closer to answering fundamental questions about our cosmic neighborhood and our place within it. The habitable zone, also known as the Goldilocks zone, is the region around a star where conditions could be just right for liquid water to exist on the surface of a planet. This zone is crucial in the search for life because water is considered essential for life as we know it. Planets in the habitable zone receive enough energy from their star to maintain temperatures that allow water to remain liquid on their surface. Too close to the star, and water would boil away. Too far, and it would freeze solid. The exact boundaries of this zone depend on factors such as the star's size, temperature, and the planet's atmosphere. Scientists focus on planets within the habitable zone when searching for potential alien life. These worlds are prime candidates for hosting organisms similar to those found on Earth. However, being in the habitable zone does not guarantee a planet will support life. Other factors, such as the planet's size, composition, and magnetic field, also play crucial roles. The concept of the habitable zone has expanded our understanding of where life might exist in the universe. It has guided astronomers in their search for exoplanets and has helped narrow down the vast number of celestial bodies to those most likely to harbor life. This focused approach increases our chances of detecting biosignatures, chemical markers that could indicate the presence of life on distant worlds. As we explore the cosmos, astronomers have discovered several intriguing exoplanets that share similarities with Earth. One of the most promising is Kepler 442b, located about 1,200 light-years away. This planet orbits a star similar to our Sun and lies within the habitable zone where liquid water could exist on its surface. Another candidate is Proxima Centauri b, which orbits the closest star to our solar system, just over 4 light-years away. While smaller than Earth, it receives a similar amount of energy from its star, making it a tantalizing target for future study. TRAPPIST 1e, part of a system of 7 Earth-sized planets, has also captured scientists' attention. It is similar in size and density to Earth and might have a rocky composition. The planet TOI 700 is another noteworthy discovery, estimated to be 20% larger than Earth and potentially able to support liquid water on its surface. These exoplanets offer exciting possibilities for understanding planetary formation and the potential for life beyond our solar system. However, it is important to note that while these worlds share some characteristics with Earth, we still have much to learn about their atmospheres, compositions, and potential habitability. Scientists employ several ingenious methods to uncover the secrets of exoplanets, those distant worlds orbiting stars beyond our solar system. One primary technique is transit spectroscopy, which analyzes the light from a star as an exoplanet passes in front of it. As the planet transits, some of the starlight filters through its atmosphere. Different elements and compounds in the atmosphere absorb specific wavelengths of light, creating a unique spectral fingerprint. By studying these absorption patterns, scientists can deduce the presence of various gases and estimate their abundances. Another powerful tool is direct imaging, which captures actual pictures of exoplanets. This method works best for young, hot planets that emit infrared radiation, making them easier to detect against the glare of their host star. Advanced telescopes equipped with coronagraphs or star shades can block out the star's light, allowing astronomers to analyze the planet's own glow. The spectrum of this light provides clues about the planet's temperature, size, and atmospheric composition. Astronomers also use a technique called radial velocity to study exoplanets. While this method primarily detects planets by measuring their gravitational effects on their host stars, it can also provide insights into planetary composition. By combining radial velocity data with other observations, scientists can estimate a planet's density, which helps determine whether it is predominantly rocky, gaseous, or something in between. As technology advances, new methods are emerging. Space-based telescopes like the James Webb Space Telescope are pushing the boundaries of exoplanet research, offering unprecedented sensitivity and resolution. These cutting-edge instruments allow scientists to probe ever deeper into the atmospheres of distant worlds, searching for signs of habitability and even potential biosignatures that could indicate the presence of life. The Fermi paradox addresses a puzzling question in our quest to understand our place in the universe. Given the vast number of stars and planets in our galaxy and the age of the universe, one might expect that intelligent life should be common. Yet, we have not detected any signs of extraterrestrial civilizations. This apparent contradiction between the high probability of alien life and the lack of evidence for it is what we call the Fermi paradox. This concept is named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a discussion about extraterrestrial life. The paradox challenges our assumptions about the prevalence of life in the cosmos and forces us to consider various explanations for the silence we observe. The Fermi paradox directly impacts our search for extraterrestrial intelligence. It prompts scientists to refine their methods and expand their search criteria. Researchers now explore a wide range of possibilities, from detecting artificial radio signals to looking for signs of advanced technology around distant stars. Some proposed solutions to the Fermi paradox suggest that intelligent life might be rare, short-lived, or uninterested in communication. Others speculate that advanced civilizations might be difficult to detect, or that we simply have not been looking in the right places or for long enough. As we continue to explore our galaxy and improve our detection methods, we edge closer to potentially resolving this intriguing paradox and answering one of humanity's most profound questions. Are we alone in the universe? Biosignatures are detectable signs that indicate the presence of life, past or present. These can be chemical, physical, or geological markers that are uniquely produced by living organisms. On other planets, biosignatures could provide compelling evidence for extraterrestrial life. One key biosignature is the presence of certain gases in a planet's atmosphere. For example, oxygen and methane existing together in an atmosphere is a strong indicator of life, as these gases quickly react with each other and would not persist without continuous replenishment from biological processes. Similarly, the detection of gases like nitrous oxide or dimethyl sulfide, which on Earth are primarily produced by living organisms, could suggest biological activity on other worlds. Another type of biosignature is the presence of complex organic molecules. While some organic compounds can form through non-biological processes, the detection of a diverse array of complex organics, especially those with specific chirality or handedness, would be a compelling sign of life. Additionally, certain mineral formations, such as stromatolites on Earth, can serve as fossilized evidence of ancient microbial life. Scientists are developing increasingly sophisticated methods to detect these biosignatures from afar. Telescopes and space probes can analyze the light passing through a planet's atmosphere to determine its composition, potentially revealing telltale signs of life. Future missions will also search for visual clues on planetary surfaces, such as changes in reflectivity that could indicate vegetation or other biological processes. The hunt for biosignatures represents one of the most exciting frontiers in the search for life beyond Earth. Extremophiles, organisms that thrive in extreme environments on Earth, provide crucial insights for astrobiologists searching for life beyond our planet. These remarkable creatures, adapted to conditions once thought incompatible with life, expand our understanding of where organisms might exist in the cosmos. By studying extremophiles in deep-sea hydrothermal vents, scientists have discovered life forms that do not rely on sunlight for energy. Instead, they use chemosynthesis, deriving energy from chemical reactions in their harsh environment. This discovery suggests that life could potentially exist in the dark oceans beneath the icy surfaces of moons like Europa or Enceladus. Extremophiles found in highly acidic or alkaline environments, such as the geothermal pools of Yellowstone National Park, demonstrate that life can adapt to chemical conditions vastly different from those typically associated with habitability. This adaptability expands the range of potentially life-supporting environments on other worlds, including planets with atmospheres or surface compositions unlike Earth's. The resilience of tardigrades, microscopic animals that can survive the vacuum of space, extreme temperatures, and high levels of radiation, provides valuable information about the potential for life to withstand interplanetary travel or exist on worlds with harsh surface conditions. These studies help scientists refine their search parameters and develop more effective tools for detecting potential biosignatures on other planets and moons in our solar system and beyond. Space agencies and astronomers are developing exciting new tools to hunt for worlds beyond our solar system and potential alien life. The James Webb Space Telescope, launched in late 2021, is now peering into exoplanet atmospheres with unprecedented detail. Its powerful infrared instruments can detect the chemical signatures of water, methane, and other potential biosignatures. Several ground-based megatelescopes are also under construction, including the extremely large telescope in Chile. With main mirrors spanning 30 to 40 meters wide, these behemoths will directly image some exoplanets and analyze their light. The Nancy Grace Roman Space Telescope, set to launch later this decade, will use both transit and direct imaging methods to catalog thousands of new worlds. Looking further ahead, proposed missions like LUVOIR or HabEx would use advanced coronagraphs and starshades to block out the glare of host stars, revealing smaller, rocky planets in habitable zones. These could potentially photograph Earth-like worlds and search for signs of vegetation or industrial pollutants that might indicate intelligent life. Breakthroughs in propulsion technology may eventually allow us to send probes to nearby star systems. Innovative concepts like light sails pushed by powerful lasers could potentially reach Alpha Centauri within decades, beaming back close-up data on any planets orbiting our stellar neighbors. The search for life beyond Earth is entering an exciting new era of discovery. Life on other planets could be vastly different from what we observe on Earth. While Earth-based life relies on carbon, water, and DNA, alien life might use entirely different chemical foundations. Some scientists speculate about the possibility of silicon-based life forms, which could thrive in extremely hot environments where carbon-based life would perish. Extraterrestrial organisms might also have wildly different metabolic processes. Instead of oxygen, they could breathe hydrogen, methane, or even sulfur compounds. Their energy sources might not be sunlight or chemical reactions we're familiar with, but could involve harnessing energy from thermal vents, radiation, or even gravitational forces. The physical forms of alien life could be unrecognizable to us. They might not be discrete organisms, but exist as vast networks or colonies. Some could be microscopic, while others might be planet-sized entities. They could perceive and interact with their environment through senses we can't even imagine, detecting quantum fluctuations or gravitational waves. Even the concept of life itself might need redefinition when we encounter alien biology. What we consider essential characteristics of life, such as reproduction or evolution, might manifest in completely unfamiliar ways on other worlds. The boundary between living and non-living might be blurred, challenging our fundamental understanding of what it means to be alive. Our solar system began its journey about 4.5 billion years ago, emerging from a vast cloud of gas and dust in space. This cosmic nursery, known as a solar nebula, contained the remnants of earlier stars that had lived and died, scattering their elements across the cosmos. As gravity worked its magic, the nebula began to collapse inward, spinning faster and flattening into a disk. At the center of this swirling maelstrom, intense pressure and heat ignited nuclear fusion, giving birth to our Sun. The young star's powerful radiation and solar winds pushed lighter elements outward while leaving heavier materials closer to the center. Over time, the remaining dust and gas in the disk began to clump together, forming countless planetesimals. These small, rocky bodies collided and merged, growing larger and larger. The inner planets, including Earth, formed from metal and rock, while the outer planets accumulated vast amounts of gas and ice. This process of accretion and collision continued for millions of years, sculpting the solar system we see today. Leftover debris became asteroids, comets, and other small bodies, completing the rich tapestry of our cosmic neighborhood. Our solar system is a vast cosmic neighborhood centered around our star, the Sun. At its heart, the Sun exerts a powerful gravitational influence, holding the entire system together. Orbiting this celestial anchor are 8 planets, each unique in its composition and characteristics. Mercury, Venus, Earth, and Mars form the inner rocky planets, while Jupiter, Saturn, Uranus, and Neptune comprise the outer gaseous giants. Scattered throughout the solar system are smaller bodies that add to its complexity. Dwarf planets, including Pluto, Eris, and Ceres, occupy various regions. Countless asteroids, primarily concentrated in the asteroid belt between Mars and Jupiter, hurtle through space. Comets, often described as cosmic snowballs, originate from the outer reaches and occasionally grace our skies with their spectacular tails. Moons, the natural satellites of planets, are abundant in our solar system. From Earth's solitary companion to the dozens of moons orbiting the gas giants, these celestial bodies come in a wide array of sizes and compositions. Some, like Jupiter's Europa and Saturn's Enceladus, even hold the potential for subsurface oceans and possible extraterrestrial life. Beyond the planets lies the Kuiper Belt, a region of icy bodies and potential dwarf planets. Even further out, the hypothesized Oort cloud marks the outer boundary of our solar system, a spherical shell of icy objects thought to extend nearly a quarter of the way to the nearest star. Together, these components create a dynamic and intricate system, each playing a role in the cosmic dance around our Sun. The planets in our solar system are divided into 2 distinct groups: the inner planets and the outer planets. These groups differ significantly in their composition and characteristics, reflecting the conditions under which they formed billions of years ago. The inner planets, also known as terrestrial planets, consist of Mercury, Venus, Earth, and Mars. These worlds are relatively small and dense, with solid, rocky surfaces. They are primarily composed of heavy elements like iron, nickel, and silicates. The inner planets have few or no moons and lack prominent ring systems. Their atmospheres, when present, are relatively thin and composed mainly of carbon dioxide, nitrogen, and in Earth's case, life-sustaining oxygen. In contrast, the outer planets, often called gas giants, include Jupiter, Saturn, Uranus, and Neptune. These behemoths are significantly larger and less dense than their inner counterparts. They are predominantly composed of lighter elements such as hydrogen and helium, with small rocky cores. The outer planets boast extensive systems of rings and numerous moons. Their thick atmospheres are made up of hydrogen, helium, and various ices, creating distinct bands and swirling storm systems visible from Earth through telescopes. These differences in composition and characteristics between the inner and outer planets provide valuable insights into the formation and evolution of our solar system, helping scientists better understand the processes that shape the worlds around us. The Kuiper Belt is a vast region of space that extends beyond the orbit of Neptune, the 8th planet from the Sun. This celestial zone forms a disk-like band in the outer reaches of our solar system, spanning from about 30 to 50 astronomical units from the Sun. An astronomical unit is the average distance between Earth and the Sun. This remote area is home to a multitude of icy bodies, remnants from the early formation of our solar system. These objects, known as Kuiper Belt objects or KBOs, are primarily composed of frozen volatiles such as methane, ammonia, and water. The most famous residents of the Kuiper Belt are dwarf planets, including Pluto, Eris, Makemake, and Haumea. Aside from dwarf planets, the Kuiper Belt contains countless smaller icy bodies, often referred to as planetesimals. These range in size from small boulders to objects hundreds of kilometers in diameter. Many short-period comets originate from this region, their orbits occasionally altered by gravitational interactions, sending them hurtling into the inner solar system. Scientists believe the Kuiper Belt holds valuable clues about the early solar system's formation and evolution. By studying these distant, pristine objects, Researchers hope to gain insights into the conditions and processes that shaped our cosmic neighborhood billions of years ago. The exploration of the Kuiper Belt continues to reveal new surprises, expanding our understanding of the solar system's outer frontier. The Oort cloud is a vast, spherical region surrounding our solar system, extending from about 1,500 to 100,000 times the distance between Earth and the Sun. This enormous cloud is believed to contain trillions of icy bodies, ranging in size from small rocks to objects as large as mountains. These frozen remnants are leftovers from the formation of our solar system, preserving ancient material from the early days of our cosmic neighborhood. Comets are intimately connected to the Oort cloud, as this region serves as their primary reservoir. When gravitational disturbances, such as the passage of a nearby star or the movement of galactic tides, nudge these icy bodies, some begin long journeys toward the inner solar system. As they approach the Sun, the heat causes their icy surfaces to sublimate, creating the characteristic coma and tail that make comets so distinctive. The Oort cloud explains the origins of long-period comets, those with orbital periods exceeding 200 years. These comets often have highly elliptical orbits that take them deep into the outer reaches of the solar system. Short-period comets, in contrast, originate primarily from the closer Kuiper Belt, a disc-shaped region beyond Neptune's orbit. Understanding the Oort cloud and its relationship to comets provides crucial insights into the history and dynamics of our solar system. By studying these distant, icy bodies, scientists can unravel the mysteries of planetary formation and the evolution of our cosmic environment over billions of years. Planetary rings are fascinating structures that form through a variety of processes. The most common mechanism involves the breakup of moons or other celestial bodies that venture too close to a planet. When an object enters a planet's Roche limit, the gravitational forces from the planet overcome the object's internal cohesion, causing it to disintegrate. The resulting debris spreads out to form a ring system around the planet. Another way rings can form is through the ejection of material from a planet's surface or atmosphere. This can occur during impact events or through volcanic activity on moons orbiting the planet. Over time, this ejected material can settle into stable orbits, creating rings. In our solar system, all 4 gas giants possess ring systems, albeit with varying degrees of prominence. Saturn boasts the most spectacular and well-known rings, visible even through small telescopes from Earth. Jupiter, Uranus, and Neptune also have ring systems, though they are much fainter and were only discovered relatively recently through space missions and advanced Earth-based observations. Interestingly, Earth might have had a ring system in its distant past. Some scientists theorize that the collision which formed our moon could have initially created a ring of debris around our planet. This ring would have eventually coalesced to form the moon we see today. The dynamic nature of ring systems reminds us that our solar system is constantly evolving, with cosmic processes occurring on timescales far beyond human experience. Our solar system boasts an impressive array of moons, each with its own distinct characteristics. Jupiter, the largest planet, hosts 4 major moons known as the Galilean satellites: Io, Europa, Ganymede, and Callisto. Io stands out for its intense volcanic activity, constantly reshaping its surface with eruptions and lava flows. Europa fascinates scientists with its smooth, icy exterior, concealing a potentially habitable subsurface ocean. Saturn's diverse collection of moons includes Titan, the only moon in our solar system with a dense atmosphere and liquid on its surface, though in the form of methane lakes rather than water. Enceladus, another Saturnian moon, features icy geysers erupting from its south pole, hinting at a subsurface ocean that could harbor life. Uranus and Neptune, the ice giants, have their own lunar companions. Uranus's Miranda showcases a bizarre patchwork terrain, suggesting a violent past of collisions and reformations. Neptune's Triton, likely a captured Kuiper Belt object, orbits the planet in a retrograde direction and has nitrogen geysers erupting from its icy surface. Even our own moon holds unique significance as the only celestial body humans have set foot on beyond Earth. Its gravitational influence stabilizes Earth's axial tilt, contributing to our planet's relatively stable climate over long periods. Asteroids and comets are both celestial bodies orbiting our Sun, but they have distinct characteristics and origins. Asteroids are primarily rocky or metallic objects, often described as leftover building blocks from the formation of our solar system. They typically orbit in the region between Mars and Jupiter, known as the asteroid belt. Comets, on the other hand, are composed of ice, dust, and rocky material. They originate from the outer reaches of the solar system in areas like the Kuiper belt and the hypothesized Oort cloud. The most noticeable difference between asteroids and comets is their behavior as they approach the Sun. Asteroids generally maintain their appearance, while comets undergo dramatic changes. As a comet nears the Sun, its icy components begin to sublimate, creating a glowing coma around the nucleus and often producing a spectacular tail of gas and dust that can stretch for millions of kilometers. Both asteroids and comets play crucial roles in our understanding of the solar system. They serve as time capsules, preserving material from the early stages of our cosmic neighborhood. Scientists study these objects to gain insights into the conditions present during the formation of planets and other celestial bodies. Additionally, both asteroids and comets have impacted Earth throughout its history, delivering water and organic compounds that may have been essential for the development of life on our planet. These celestial wanderers also pose potential risks to Earth. While most asteroids and comets pose no threat, monitoring and studying these objects helps us prepare for the possibility of future impacts. This ongoing vigilance has led to advancements in our ability to detect and track near-Earth objects, contributing to our overall understanding of celestial mechanics and the dynamic nature of our solar system. Pluto currently holds the status of a dwarf planet, a classification it received in 2006. This reclassification came after decades of debate within the astronomical community about the nature of celestial bodies in our solar system. The decision to change Pluto's status stemmed from our expanding knowledge of the outer solar system. As we discovered more objects beyond Neptune, it became clear that Pluto was just one of many similarly sized bodies in that region. The Kuiper belt, where Pluto resides, is home to numerous icy objects, some of which rival or even exceed Pluto in size. The International Astronomical Union, the organization responsible for naming and classifying celestial objects, established new criteria for planethood. To be considered a planet, an object must orbit the Sun, have enough mass to achieve a nearly round shape, and have cleared its orbital neighborhood of other objects. While Pluto meets the first two criteria, it fails the third, as its orbit intersects with that of Neptune, and it shares its neighborhood with other Kuiper belt objects. This reclassification has sparked continued discussion and some controversy in both scientific and public spheres. Some argue that the definition is too restrictive, while others see it as a necessary step in better understanding and categorizing the diverse objects in our solar system. Regardless of its official status, Pluto remains a fascinating world, with its own moons and unique characteristics that continue to intrigue scientists and space enthusiasts alike. The Sun exerts a profound influence on the dynamics of our solar system, acting as the gravitational anchor that holds everything together. Its immense mass, over 300,000 times that of Earth, creates a powerful gravitational field that extends far beyond the orbit of Neptune. This gravitational pull keeps planets, dwarf planets, asteroids, and comets in their orbits, preventing them from drifting off into interstellar space. Beyond gravity, the Sun's energy output shapes the environment of the entire solar system. Its constant stream of charged particles, known as the solar wind, interacts with planetary atmospheres and magnetic fields, creating phenomena like auroras on Earth and other planets. This solar wind also carves out a vast bubble in interstellar space called the heliosphere, which defines the boundary of our solar system. The sun's radiation heats planetary surfaces and atmospheres, driving weather patterns and climate systems. Its ultraviolet light interacts with molecules in upper atmospheres, influencing their composition and behavior. Even the chemical makeup of comets is affected as they approach the sun, with solar heat causing ices to sublimate and form the characteristic coma and tail. Solar activity, including sunspots, solar flares, and coronal mass ejections, can have far-reaching effects. These events can disrupt satellite communications, affect space weather, and even impact Earth's climate over long timescales. The sun's influence truly permeates every aspect of our solar system, from the largest planets to the smallest particles of interplanetary dust. The dawn of space exploration marked a pivotal moment in human history. In 1957, the Soviet Union launched Sputnik 1, the first artificial satellite to orbit Earth. This breakthrough ignited the space race between the United States and the Soviet Union, spurring rapid advancements in space technology. A mere month later, the Soviets achieved another milestone by sending the first living creature into orbit. Laika, a small dog, became the first animal to journey into space aboard Sputnik 2. Although she did not survive the mission, her flight paved the way for human spaceflight. The United States responded with its own achievements. In 1958, NASA was established, and the following year, the Mercury program began. This initiative aimed to put the first American in space. Success came in 1961 when Alan Shepard became the first American to reach space in Freedom 7. That same year, Soviet cosmonaut Yuri Gagarin achieved a monumental feat by becoming the first human to orbit Earth in Vostok 1. This historic flight lasted 108 minutes and marked the beginning of human presence in space. These early milestones set the stage for the incredible space exploration achievements that would follow in the coming decades. Space exploration technology has undergone remarkable advancements since the first space missions. In the early days, spacecraft were rudimentary, relying on basic propulsion systems and limited onboard computers. The Apollo missions that landed humans on the moon used computers with less processing power than a modern smartphone. Today, spacecraft are equipped with sophisticated systems that allow for precise navigation, enhanced communication, and advanced scientific instruments. Propulsion technology has evolved from chemical rockets to include ion engines, which use electrical fields to accelerate charged particles, providing more efficient long-distance travel. Solar panels have become more efficient, allowing spacecraft to operate for extended periods in deep space. Robotic exploration has become increasingly important, with rovers like Curiosity and Perseverance on Mars capable of conducting complex scientific experiments and transmitting data back to Earth. These rovers are equipped with high-resolution cameras, spectrometers, and even tools to collect and analyze samples. Space telescopes have revolutionized our understanding of the universe. The Hubble Space Telescope, launched in 1990, has provided unprecedented views of distant galaxies, while newer telescopes like the James Webb Space Telescope can observe the universe in infrared light, revealing previously hidden cosmic phenomena. These technological leaps have expanded our knowledge of the cosmos and paved the way for future exploration of our solar system and beyond. Space exploration has yielded numerous groundbreaking discoveries that have revolutionized our understanding of the universe. One of the most significant findings is the detection of exoplanets, planets orbiting stars beyond our solar system. This discovery has opened up new possibilities in the search for habitable worlds and potential extraterrestrial life. Another crucial revelation came from the Hubble Space Telescope, which provided evidence for the accelerating expansion of the universe. This led to the concept of dark energy, a mysterious force that counteracts gravity on cosmic scales. The discovery of cosmic microwave background radiation further supported the Big Bang theory, offering insights into the early stages of our universe. Space missions have also transformed our knowledge of our own solar system. The Cassini mission to Saturn revealed complex systems of rings and moons, including Enceladus with its subsurface ocean. Mars rovers have found evidence of ancient water on the red planet, suggesting it may have once harbored life. Perhaps one of the most awe-inspiring achievements is the direct imaging of a black hole by the Event Horizon Telescope. This feat confirmed predictions made by Einstein's theory of general relativity and provided visual evidence of these enigmatic cosmic objects. These discoveries have not only expanded our scientific knowledge, but also fueled our curiosity about the vast cosmos that surrounds us. Space agencies approach planetary missions with meticulous planning and execution. The process begins years before launch, with scientists and engineers collaborating to define mission objectives and design spacecraft capable of withstanding the harsh conditions of space travel. Mission planners must consider numerous factors, including the positions of planets, launch windows, and the most efficient trajectories. They use advanced computer simulations to plot courses that minimize fuel consumption and travel time. These calculations are crucial, as even small errors can result in a spacecraft missing its target by millions of kilometers. The spacecraft itself undergoes rigorous testing to ensure it can survive the extreme temperatures, radiation, and vacuum of space. Engineers subject components to simulated space conditions, vibration tests, and other stressors to identify and resolve potential issues before launch. Once the mission is underway, a dedicated team monitors the spacecraft around the clock, making course corrections and troubleshooting problems as they arise. Communication with distant probes can take hours, requiring careful planning and anticipation of potential challenges. This ongoing process of monitoring and adjustment continues throughout the mission, ensuring valuable scientific data is collected and transmitted back to Earth. Long-duration space travel presents numerous challenges for both astronauts and spacecraft. One of the primary concerns is the effect of microgravity on the human body. Extended periods in weightlessness can lead to muscle atrophy and bone density loss, potentially weakening astronauts over time. This physical deterioration requires specialized exercise equipment and rigorous daily routines to counteract. Radiation exposure poses another significant risk. Beyond Earth's protective magnetosphere, astronauts are subjected to higher levels of cosmic radiation, which can damage DNA and increase the risk of cancer. Developing effective shielding technologies is crucial for safeguarding crew health during extended missions. Psychological factors also play a critical role in long-duration space travel. Astronauts must cope with isolation, confinement, and the stress of living in a dangerous environment for months or even years. Maintaining mental health and crew cohesion becomes paramount, necessitating careful crew selection and support systems. Technical challenges abound as well. Spacecraft must be designed to function reliably for extended periods without the possibility of external maintenance. Life support systems need to recycle air and water efficiently, while food supplies must be carefully managed. Additionally, the immense distances involved in interplanetary travel require advanced propulsion systems and precise navigation to ensure mission success. Life aboard the International Space Station is a unique experience that challenges astronauts in ways unlike anything on Earth. The station orbits our planet at an altitude of about 250 miles, traveling at over 17,000 miles per hour. In this extraordinary environment, astronauts must adapt to the absence of gravity, which affects every aspect of their daily lives. Astronauts float freely inside the station, using handrails to navigate between modules. Simple tasks like eating, sleeping, and personal hygiene require special techniques and equipment. Food comes in sealed packages and must be rehydrated or heated. Water is a precious resource, recycled from various sources, including sweat and urine. Astronauts sleep in small crew quarters, securing themselves in sleeping bags to prevent drifting. Work on the station revolves around scientific experiments, maintenance, and communication with ground control. Astronauts conduct research in fields such as biology, physics, and Earth observation. They also maintain the station's systems, perform repairs, and occasionally venture outside for spacewalks to install new equipment or make upgrades. Exercise is crucial in space to counteract muscle and bone loss caused by microgravity. Astronauts spend about 2 hours each day working out on specialized equipment. Despite the challenges, many astronauts describe their time on the station as a transformative experience, offering unparalleled views of Earth and a unique perspective on our place in the universe. Space agencies around the world have ambitious plans to explore our cosmic neighborhood in the coming years. NASA's Dragonfly mission aims to send a rotorcraft to Saturn's largest moon, Titan. This unique probe will fly through Titan's dense atmosphere, exploring its surface and searching for signs of potential life in its methane lakes and organic-rich environment. The European Space Agency is developing the Jupiter Icy Moons Explorer, or JUICE, to study Jupiter and 3 of its largest moons, Ganymede, Callisto, and Europa. This mission will focus on investigating the potential for liquid water oceans beneath the icy surfaces of these moons, which could harbor the conditions necessary for life. Looking closer to home, several nations are planning missions to Mars. China aims to return Martian samples to Earth by 2028, while NASA and the European Space Agency are collaborating on a similar endeavor. These sample return missions could provide unprecedented insights into the red planet's geology and potential for past or present microbial life. Venturing to the outer solar system, NASA's proposed Trident mission would explore Neptune's largest moon, Triton. This mysterious world, with its unique retrograde orbit and active geology, could offer clues about the formation and evolution of ice giants and their moons. These future missions promise to expand our understanding of our solar system and potentially reshape our views on the prevalence of life in the cosmos. Establishing a permanent human presence on the Moon or Mars presents significant challenges, but ongoing research and technological advancements are bringing this goal closer to reality. For the Moon, the first step would likely involve creating a base at one of the lunar poles, where there is evidence of water ice in permanently shadowed craters. This water could be extracted and processed to provide drinking water, oxygen for breathing, and hydrogen for fuel. On Mars, the approach would be similar, but more complex due to the greater distance and harsher conditions. Initial habitats would likely be constructed using a combination of prefabricated modules sent from Earth and local materials. Martian soil could be used to create radiation shielding, while underground lava tubes might offer natural protection from cosmic rays and extreme temperature fluctuations. In both cases, developing sustainable life support systems is crucial. This includes technologies for recycling air and water, growing food, and managing waste. Energy would be generated through a combination of solar panels and nuclear power sources, with the latter being especially important on Mars due to its greater distance from the Sun and frequent dust storms. Long-term survival on these worlds would also require the ability to manufacture replacement parts and equipment on-site, reducing reliance on resupply missions from Earth. This could be achieved through advanced three-dimensional printing technologies and the development of processes to utilize local resources, a concept known as in situ resource utilization. Private companies have become increasingly important players in modern space exploration, revolutionizing the industry and complementing the efforts of government space agencies. These companies, often referred to as commercial space firms, are driving innovation and reducing costs in various aspects of space technology and exploration. One of the most significant contributions of private companies is in the development of reusable rocket technology. This advancement has dramatically lowered the cost of launching payloads into orbit, making space more accessible for a wider range of purposes. Private firms are also pioneering new spacecraft designs, including those capable of carrying humans to low Earth orbit and potentially beyond. Commercial space companies are actively involved in satellite deployment, providing crucial services for communication, Earth observation, and scientific research. They are developing space stations and planning for future lunar and Martian missions, often in partnership with national space agencies. This collaboration between public and private sectors is fostering a new era of space exploration, combining government resources and oversight with private sector agility and innovation. The involvement of private companies has also sparked public interest in space exploration, attracting investment and inspiring a new generation of scientists and engineers. As these firms continue to push boundaries and develop new technologies, they are shaping the future of human activity in space, from space tourism to potential off-world resource utilization. Space exploration has revolutionized life on Earth in countless ways. The technologies developed for space missions have found numerous applications in our daily lives. For instance, satellite technology, originally designed for communication in space, now enables global telecommunications, weather forecasting, and navigation systems used by millions every day. Medical advancements have also stemmed from space research. Techniques developed to monitor astronauts' health have led to improved medical imaging and diagnostic tools on Earth. Water purification systems created for spacecraft now provide clean water in remote areas and disaster zones. Even everyday items like memory foam mattresses and scratch-resistant lenses were originally developed for space applications. Space exploration has significantly enhanced our understanding of Earth itself. Satellite observations allow us to track climate change, monitor natural disasters, and manage resources more effectively. This bird's-eye view of our planet has been instrumental in shaping environmental policies and conservation efforts worldwide. Moreover, the pursuit of space exploration inspires scientific curiosity and technological innovation. It drives advancements in fields such as robotics, materials science, and computer technology. These innovations often find their way into various industries, boosting economic growth and improving quality of life on Earth. The benefits of space exploration continue to ripple through society, touching almost every aspect of our modern world. Gamma-ray bursts are the most powerful explosions known in the universe. These intense flashes of high-energy radiation outshine entire galaxies for brief moments, releasing more energy in seconds than our Sun will emit in its entire lifetime. These cosmic phenomena occur when massive stars collapse at the end of their lives or when two ultra-dense neutron stars collide. In the case of collapsing stars, the core implodes, forming a black hole, while the outer layers are violently ejected. This process creates two narrow beams of intense radiation that shoot out from the poles of the newly formed black hole at nearly the speed of light. When neutron stars merge, they spiral together in a cataclysmic event, producing gravitational waves and an explosion that rivals the power of a supernova. This collision also generates a short, intense burst of gamma rays, along with other forms of electromagnetic radiation. Scientists detect these bursts using space-based observatories that constantly monitor the sky. When a burst is detected, astronomers quickly pivot other telescopes to study the afterglow, which can last for hours or even days. These observations help researchers unravel the mysteries of these extreme cosmic events and gain insights into the early universe. Solar flares are powerful bursts of energy from the Sun that can have significant impacts on Earth and our technology. These intense explosions release a flood of electromagnetic radiation, including X-rays and ultraviolet light, which travel at the speed of light and reach Earth in about 8 minutes. When this radiation arrives, it can cause disruptions to our upper atmosphere, interfering with radio communications and satellite operations. The ionosphere, a layer of charged particles in our upper atmosphere, becomes more ionized, which can affect the transmission of radio waves used for communication and navigation. Solar flares are often accompanied by coronal mass ejections, massive clouds of solar plasma that can trigger geomagnetic storms upon reaching Earth. These storms can induce electrical currents in power grids, potentially causing widespread blackouts. They also pose risks to satellites, potentially damaging their electronics or altering their orbits. While solar flares can cause problems, they also create beautiful auroras as charged particles interact with Earth's magnetic field. Scientists constantly monitor the sun to predict solar flares and prepare for their effects, helping to protect our technology and infrastructure from these powerful solar events. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. These particles, primarily protons and atomic nuclei, originate from sources both within and beyond our galaxy. They constantly bombard Earth's atmosphere, creating cascades of secondary particles that shower down to the planet's surface. The origins of cosmic rays have long puzzled scientists. Some cosmic rays come from our own sun, especially during solar flares and coronal mass ejections. However, the most energetic cosmic rays have sources far beyond our solar system. Supernova explosions, the violent deaths of massive stars, are believed to be a significant source of these high-energy particles. The immense shock waves produced by these stellar explosions can accelerate particles to incredible speeds. Other potential sources of cosmic rays include active galactic nuclei, where supermassive black holes at the centers of galaxies eject powerful jets of particles, and pulsars, rapidly rotating neutron stars with intense magnetic fields. Some of the most energetic cosmic rays may even originate from sources outside our Milky Way galaxy, traveling vast intergalactic distances before reaching Earth. Studying cosmic rays helps scientists understand the most extreme and energetic processes in the universe. These particles carry information about their sources and the environments they have traveled through, providing valuable insights into the nature of our cosmos and the forces that shape it. Magnetars are a rare type of neutron star, the incredibly dense remnants left behind after massive stars explode as supernovae. These cosmic objects are considered among the most extreme in the universe due to their unparalleled magnetic fields, which are the strongest known in the cosmos. To put this in perspective, a magnetar's magnetic field is about 1 quadrillion times stronger than Earth's magnetic field. This intense magnetism gives magnetars their name and extraordinary properties. The magnetic field is so powerful that it can distort the quantum structure of atoms and molecules, making conventional matter as we know it impossible on their surface. If a magnetar were located halfway to the moon, it could erase the magnetic strips on all credit cards on Earth. Magnetars also exhibit violent behavior, occasionally producing enormous bursts of energy called giant flares. These flares can release more energy in a fraction of a second than our sun does in hundreds of thousands of years. Such events can be detected across vast cosmic distances and have been observed in other galaxies. The extreme nature of magnetars makes them invaluable to scientists studying the limits of physics. They serve as natural laboratories for testing theories about matter, energy, and the fundamental forces of the universe under conditions impossible to replicate on Earth. As we continue to observe and study these enigmatic objects, they promise to reveal more about the most extreme phenomena in the cosmos. Planetary nebulae form during the final stages of a star's life, specifically for stars similar in mass to our Sun. As these stars exhaust their nuclear fuel, they begin to shed their outer layers of gas into space. This ejected material expands outward, creating a glowing shell of ionized gas that surrounds the dying star at its core. The name planetary nebula is a misnomer, as these objects have nothing to do with planets. Early astronomers gave them this name because, when viewed through telescopes, they appeared as round disks similar to planets. In reality, planetary nebulae come in a variety of shapes, from spherical to butterfly-like, depending on factors such as the star's rotation and magnetic fields. These cosmic structures provide valuable insights into stellar evolution. They represent a brief but crucial phase in the life cycle of low to intermediate mass stars, lasting only a few tens of thousands of years. By studying planetary nebulae, astronomers can learn about the chemical composition of stars, as the ejected material contains elements that were forged within the star's core over its lifetime. Furthermore, Planetary nebulae play a vital role in galactic evolution. They enrich the interstellar medium with heavier elements, which will eventually be incorporated into new stars and planets. This process of stellar recycling is fundamental to the ongoing evolution of galaxies and the universe as a whole. Gravitational waves are ripples in the fabric of space-time caused by some of the most energetic events in the universe. These waves travel at the speed of light and carry information about their dramatic origins, such as colliding black holes or neutron stars. The first direct detection of gravitational waves occurred on September 14, 2015, by the Laser Interferometer Gravitational Wave Observatory, known as LIGO. This groundbreaking discovery confirmed a major prediction of Albert Einstein's general theory of relativity, proposed a century earlier. LIGO consists of two enormous L-shaped detectors in Louisiana and Washington state. Each arm of the L is 4 kilometers long and contains a powerful laser beam. When a gravitational wave passes through, it causes minute changes in the length of these arms, which scientists can measure with incredible precision. The specific gravitational waves detected in 2015 were produced by two black holes, each about 30 times the mass of our Sun, spiraling towards each other and merging in a distant galaxy. This cosmic collision released an enormous amount of energy in the form of gravitational waves, which traveled across the universe for over 1 billion years before reaching Earth and making scientific history. Dark energy is a mysterious force that permeates all of space, exerting a negative pressure that causes the universe to expand at an accelerating rate. Unlike gravity, which pulls matter together, dark energy acts as a repulsive force, pushing everything apart on cosmic scales. Scientists discovered the existence of dark energy in the late 1990s when they observed that distant supernovae were farther away than expected. This revelation suggested that the expansion of the universe was speeding up rather than slowing down as previously thought. The influence of dark energy on the expansion of the universe is profound. As space expands, the density of matter decreases, but the density of dark energy remains constant. This means that over time, dark energy becomes increasingly dominant, causing the expansion to accelerate even faster. Current observations indicate that dark energy makes up about 68% of the total energy content of the universe. Despite its significant role in shaping the cosmos, the true nature of dark energy remains one of the biggest mysteries in modern physics. Scientists continue to develop theories and conduct experiments to unravel its properties and understand its origin, as it holds the key to predicting the ultimate fate of our universe. Cosmic voids are vast regions of space that contain very few or no galaxies. These enormous emptiness stretches across millions of light years, forming an integral part of the cosmic web that makes up the large-scale structure of the universe. To understand cosmic voids, we must first consider the distribution of matter in the universe. Galaxies are not spread evenly throughout space, but instead cluster together in groups and superclusters. Between these dense regions of matter lie the cosmic voids, acting as the negative space in the grand cosmic tapestry. These voids are not completely empty, however. They contain trace amounts of gas and dark matter, but at densities far lower than the cosmic average. The largest known void, called the Boötes void, spans an astonishing 300 million light-years across, large enough to fit 3,000 Milky Way galaxies inside it. Cosmic voids play a crucial role in the evolution of the universe. As matter clumps together under the force of gravity, it leaves behind these vast, empty spaces. The voids and the surrounding galaxy clusters form a foam-like structure, with the voids representing the spaces between the bubbles. This cosmic foam continues to evolve, with voids growing larger over time as gravity pulls more matter toward the dense regions, further emptying the voids in a process of cosmic self-organization. The Great Attractor is a massive gravitational anomaly located in intergalactic space, approximately 150 million light-years from Earth. This enigmatic region exerts an immense gravitational pull, influencing the motion of thousands of galaxies across a vast expanse of the universe. Its significance lies in its profound impact on cosmic structures and our understanding of large-scale galactic movements. Astronomers first detected the Great Attractor in the 1970s when they observed that our Milky Way galaxy, along with numerous other galaxies in our local group and beyond, appeared to be moving towards a specific point in space. This coherent motion, known as bulk flow, suggested the presence of an incredibly massive object or concentration of matter drawing these galaxies towards it. The true nature of the Great Attractor remains a subject of ongoing research and debate. Some scientists propose it could be a supercluster of galaxies, while others suggest it might be an even larger structure called a hypercluster. The difficulty in studying this phenomenon arises from its location behind the plane of the Milky Way, where dust and stars obstruct our view, creating a zone of avoidance for astronomical observations. Understanding the Great Attractor is crucial for cosmologists as it challenges our models of galactic distribution and movement in the universe. It provides valuable insights into the role of dark matter and dark energy in shaping cosmic structures and offers clues about the formation and evolution of the largest known objects in the cosmos. As we continue to unravel its mysteries, the Great Attractor remains a testament to the dynamic and interconnected nature of our universe. Astronomers employ a variety of sophisticated techniques to study and map the cosmic web, that vast network of filaments and voids that forms the large-scale structure of our universe. One key method involves observing the distribution of galaxies across enormous distances. By cataloging the positions of millions of galaxies, scientists can discern patterns that reveal the underlying cosmic web structure. Another crucial approach utilizes the phenomenon of gravitational lensing. As light from distant galaxies travels through space, it can be bent by the gravity of massive objects in the cosmic web. By analyzing these distortions, astronomers can infer the presence and distribution of dark matter, which forms the backbone of the cosmic web but cannot be directly observed. Spectroscopic surveys play a vital role in mapping the cosmic web as well. These surveys measure the redshift of galaxies, allowing astronomers to determine their distances and three-dimensional positions in space. This information helps create detailed maps of galaxy clusters and the filaments connecting them. Computer simulations also contribute significantly to our understanding of the cosmic web. By modeling the evolution of the universe from its earliest moments to the present day, scientists can compare their simulations with observational data, refining our knowledge of how the cosmic web formed and continues to evolve over billions of years. The ultimate fate of the universe remains a subject of intense scientific inquiry and debate. Current theories, based on our understanding of cosmic expansion and the nature of dark energy, suggest several possible scenarios for the distant future of our universe. One widely accepted theory is the concept of heat death, also known as the Big Freeze. In this scenario, the universe continues to expand indefinitely, driven by the mysterious force of dark energy. As it expands, matter and energy become increasingly spread out and diluted. Stars exhaust their fuel and die, galaxies drift apart, and black holes eventually evaporate through Hawking radiation. The universe would reach a state of maximum entropy, where no usable energy remains and no further work can be done. An alternative possibility is the Big Crunch. This theory proposes that the expansion of the universe might eventually slow down and reverse, leading to a contraction. Gravity would overcome the force of expansion, causing all matter to collapse back into an incredibly dense singularity, similar to the state before the Big Bang. However, current observations of the accelerating expansion of the universe make this scenario less likely. A third scenario, known as the Big Rip, suggests that the force of dark energy might become so strong that it overcomes all other forces, including those holding atoms together. In this case, the universe would expand so rapidly that it would literally tear itself apart, ripping galaxies, stars, planets, and even subatomic particles asunder. The exact nature of dark energy will determine whether this scenario is possible and, if so, when it might occur. The heat death of the universe is a theoretical scenario that describes the ultimate fate of our cosmos. It represents a state of maximum entropy, where all energy is evenly distributed throughout the universe, resulting in a uniform temperature approaching absolute zero. This potential end of the universe would occur gradually over an unimaginably long period. As stars exhaust their fuel and galaxies drift apart, the universe continues to expand and cool. Black holes, which initially grow by consuming matter and energy, would eventually evaporate through Hawking radiation, releasing their energy into space. In this distant future, all matter would break down into its most basic components. Atoms would disintegrate, and even subatomic particles might decay. The universe would become an impossibly vast, dark, and cold expanse, with energy spread so thinly that no work could be performed. The heat death scenario stems from the second law of thermodynamics, which states that entropy in an isolated system always increases over time. Since the universe appears to be a closed system, many scientists consider heat death a plausible ultimate fate, though other theories exist about how the universe might end. Stars will continue to form in the universe for an incredibly long time, far beyond the current age of the cosmos. The process of star formation relies on the availability of gas and dust in galaxies, particularly hydrogen, which is the most abundant element in the universe. Current estimates suggest that star formation could continue for up to 100 trillion years. This immense time span is about 7,000 times longer than the current age of the universe, which is approximately 14 billion years old. During this extended period, galaxies will gradually use up their reservoirs of gas and dust to create new stars. However, the rate of star formation will not remain constant. As time progresses, the process will slow down significantly. Larger, more massive stars burn through their fuel quickly and have relatively short lifespans. In contrast, smaller, less massive stars can shine for billions or even trillions of years. As a result, the universe will eventually be dominated by these long-lived, low-mass stars, along with stellar remnants like white dwarfs, neutron stars, and black holes. The era of star formation will come to an end when galaxies exhaust their supply of gas and dust. At this point, no new stars will be born, and the existing stars will gradually burn out, leading to a much darker and colder universe. This marks the beginning of the far future era known as the Degenerate Age, where stellar remnants and cold, dead stars will dominate the cosmic landscape. The collision of the Milky Way and Andromeda galaxies will be a cosmic dance of unimaginable scale. This galactic merger, set to occur roughly 4 billion years from now, will reshape our night sky and alter the structure of both galaxies. As these two giant spiral galaxies approach each other, their mutual gravitational pull will cause them to distort and stretch. Stars and gas clouds will be flung into new orbits, creating long tidal tails that streak across space. The collision itself will not be a single catastrophic event, but a prolonged process lasting hundreds of millions of years. Surprisingly, despite the vast number of stars in both galaxies, direct collisions between individual stars will be extremely rare due to the immense distances between them. Instead, the galaxies will pass through each other, their gas and dust clouds interacting and compressing. This compression will trigger the birth of new stars, igniting brilliant bursts of star formation across the merging galaxies. The final result of this cosmic collision will be a new, larger elliptical galaxy, sometimes dubbed Milkomeda. Our solar system is likely to survive this merger, potentially being moved to a different region of the new galaxy. The night sky, however, will be transformed, filled with the bright glow of newly formed stars and the scattered remnants of our once separate galaxies. The accelerating expansion of the universe is a profound phenomenon that will dramatically shape its future. As space itself stretches at an ever-increasing rate, galaxies and galaxy clusters will be pulled farther and farther apart. Over vast timescales, this expansion will lead to a universe that looks remarkably different from what we observe today. In the distant future, galaxies outside our local group will eventually appear to recede faster than the speed of light, due to the expansion of space itself. This means their light will never reach us, effectively disappearing from our observable universe. The night sky will gradually darken as fewer and fewer stars and galaxies remain visible. Within galaxies, the effects of expansion are counteracted by gravity, so our Milky Way and its nearest neighbors will likely remain bound together. However, these island universes will become increasingly isolated in a vast, dark cosmos. The accelerating expansion might even eventually overcome the forces holding atoms together, in a scenario known as the Big Rip. If the current acceleration continues indefinitely, the universe could face a cold and lonely fate known as the Big Freeze, or heat death. In this scenario, the universe expands to such an extent that it reaches a state of maximum entropy, where no further work or heat transfer is possible. This paints a stark picture of the potential long-term consequences of our expanding universe. The concept of a cyclic universe proposes that our cosmos undergoes endless cycles of expansion and contraction. In this model, the universe as we know it is just one phase in an eternal series of big bangs and big crunches. Each cycle begins with a rapid expansion, similar to the Big Bang theory, followed by a long period of slower expansion. Eventually, the expansion stops and reverses, leading to a big crunch where all matter collapses back into a singularity. This process then repeats, giving birth to a new universe. This idea contrasts sharply with other prevalent models, such as the widely accepted theory of an ever-expanding universe. In the expansion model, our cosmos continues to grow indefinitely, potentially leading to a cold, dark future known as the Big Freeze. Another alternative is the Big Rip scenario, where the expansion accelerates to such an extent that it tears apart the very fabric of space-time. The cyclic universe concept also differs from the steady-state theory, which suggests that the universe always looks essentially the same, with new matter constantly being created to fill the gaps as galaxies move apart. While both cyclic and steady-state models propose an eternal universe, the cyclic model includes distinct phases and dramatic changes over time. Proponents of the cyclic universe theory argue that it solves certain problems in cosmology, such as the question of what came before the Big Bang. However, it faces challenges in explaining how the universe could survive multiple cycles without increasing in entropy and eventually reaching a state of heat death. Despite these hurdles, the idea continues to intrigue scientists and spark debate in the field of cosmology. Dark energy, the mysterious force causing the accelerated expansion of our universe, plays a crucial role in shaping its future. As we continue to observe and study this enigmatic phenomenon, scientists have developed several theories about how dark energy might influence the cosmos in the long term. One possibility is that dark energy will maintain its current strength, leading to a scenario known as the Big Freeze. In this future, the universe would continue to expand at an ever-increasing rate. Galaxies would grow more distant from one another, eventually becoming so far apart that they would be invisible to each other. The night sky would gradually darken as fewer stars remained visible, and the universe would become an increasingly cold and isolated place. Another potential outcome is the Big Rip. If dark energy were to grow stronger over time, it could eventually overcome all other forces, including those holding atoms together. In this scenario, the universe would expand so rapidly that it would literally tear itself apart. Galaxies, stars, planets, and even the fundamental particles that make up matter would be ripped asunder. Conversely, if dark energy were to weaken or change its nature, we might experience a big crunch. The expansion of the universe would slow down and eventually reverse, leading to a contraction where all matter and energy collapse back into an incredibly dense state, similar to the conditions before the Big Bang. This could potentially set the stage for a new cycle of cosmic expansion and contraction. The nature of dark energy remains one of the most profound mysteries in modern cosmology, and its ultimate influence on the fate of our universe continues to captivate scientists and fuel ongoing research. The Big Crunch represents a possible fate for our universe, a cosmic finale that stands in stark contrast to the current expansion we observe. In this scenario, the expansion of the universe would eventually slow down and reverse, leading to a dramatic contraction of all matter and energy. As the universe begins to shrink, galaxies would start moving closer together rather than drifting apart. Over time, the night sky would become increasingly crowded with stars as distant galaxies draw nearer. The temperature of the universe would rise steadily as space itself contracts, causing all matter to heat up. In the final stages of the Big Crunch, the immense gravitational forces would cause larger structures like galaxies and solar systems to break apart. Stars would collide and merge, creating a cosmic firestorm of unimaginable proportions. Eventually, even atoms themselves would be unable to maintain their structure under the extreme conditions. The ultimate result of the Big Crunch would be the compression of all matter and energy in the universe into an incredibly dense, hot singularity, similar to the state theorized to have existed before the Big Bang. This raises the intriguing possibility that our universe might be part of a cyclical process of expansion and contraction, though current observations suggest that such a scenario is unlikely for our universe. The death of the last stars marks a profound turning point in the history of the universe. As these final stellar beacons fade away, they leave behind a cosmos fundamentally altered and devoid of new light sources. When the last stars exhaust their fuel and expire, the universe enters a phase astronomers call the degenerate era. During this time, stellar remnants like white dwarfs, neutron stars, and black holes dominate the galactic landscape. These dense, compact objects no longer produce the life-giving energy of their predecessors, instead slowly cooling and fading over incomprehensibly long timescales. The absence of active stars has far-reaching consequences. Without stellar furnaces to forge new elements, the production of heavy atoms ceases. The interstellar medium, once rich with gas and dust for forming new stars, becomes increasingly sparse and cold. Galaxies, no longer illuminated by billions of stars, fade into darkness, detectable only by their gravitational influence. Perhaps most significantly, the death of stars eliminates the primary source of energy and complexity in the universe. The intricate processes that depend on stellar radiation, from planet formation to the potential emergence of life, can no longer occur. The universe transitions into a quieter, darker state, marking the end of the stellar epoch and the beginning of a new chapter in cosmic evolution. As we peer into the distant future of our universe, scientists have proposed several intriguing possibilities. One prominent theory suggests a scenario called the Big Freeze, where the universe continues to expand indefinitely. In this future, stars exhaust their fuel and die out, leaving behind a cold, dark cosmos filled with black holes, neutron stars, and brown dwarfs. Another speculation involves the Big Crunch, where the expansion of the universe eventually reverses. Gravity would then pull everything back together, culminating in a hot, dense state similar to the beginning of the universe. Some theorists propose that this could lead to a cyclic model, where the universe repeatedly expands and contracts. The Big Rip presents a more dramatic end, where the expansion of the universe accelerates to such an extreme that it tears apart all matter, from galaxies down to atoms. In this scenario, even space-time itself could be shredded. A less conventional idea is the possibility of a phase transition in the vacuum of space, similar to how water can suddenly freeze into ice. This could potentially alter the fundamental laws of physics, creating an entirely new type of universe with different properties and behaviors than our own. Space-time is the fundamental fabric of our universe, combining the three dimensions of space with the dimension of time into a single, interconnected continuum. This concept, introduced by Albert Einstein in his theory of relativity, revolutionized our understanding of the cosmos. In this framework, gravity is not a force as traditionally understood, but rather the curvature of space-time itself. Massive objects, such as stars and planets, create dips or wells in the fabric of space-time, much like a heavy ball would create a depression on a stretched rubber sheet. Other objects then move along these curves, which we perceive as the effects of gravity. This relationship between space-time and gravity explains phenomena that Newtonian physics could not, such as the precise orbit of Mercury and the bending of light around massive objects. It also predicts the existence of gravitational waves, ripples in space-time caused by cataclysmic cosmic events, which were first directly detected in 2015. Understanding space-time and its connection to gravity is crucial for technologies we now take for granted, such as GPS satellites, and continues to drive our exploration of the universe, from black holes to the very structure of the cosmos itself. Einstein's theory of general relativity revolutionized our understanding of gravity. It proposes that gravity is not a force, but rather the result of the curvature of space-time caused by massive objects. This concept can be visualized by imagining space-time as a flexible fabric that bends and warps in the presence of matter and energy. According to general relativity, objects with mass create dips or wells in this cosmic fabric. The larger the mass, the deeper the well. Other objects then move along the curves created by these dips, following the path of least resistance. What we perceive as the force of gravity is actually the result of objects following these curved paths through space-time. This theory explains why planets orbit the sun and why apples fall to the ground. The Earth creates a significant curve in space-time, causing the Moon to orbit around it. Similarly, the Sun's immense mass creates an even larger distortion, influencing the orbits of all the planets in our solar system. Einstein's theory also predicts phenomena that Newtonian physics cannot explain, such as the precession of Mercury's orbit and the bending of light around massive objects. These predictions have been confirmed through observations, solidifying general relativity as our most accurate description of gravity to date. Time dilation is a fascinating phenomenon predicted by Einstein's theory of relativity. It describes how time passes at different rates for objects moving at high speeds or experiencing strong gravitational fields. Time slows down for fast-moving objects or those in strong gravitational fields compared to stationary objects or those in weaker fields. Scientists have observed time dilation in several ways. One notable example involves precise atomic clocks placed on airplanes. When these clocks are flown around the world, they show a slight time difference compared to identical clocks left on the ground. The airborne clocks tick more slowly due to their higher speed and altitude. Another striking demonstration of time dilation occurs with satellites in the Global Positioning System. These satellites orbit Earth at high speeds and experience weaker gravity than objects on the surface. As a result, time passes faster for the satellites. If this effect were not accounted for, GPS navigation would quickly become inaccurate. Perhaps the most extreme example of time dilation we've observed involves fast-moving subatomic particles called muons. These particles are created high in the atmosphere and should decay before reaching Earth's surface. However, due to their incredible speed, time slows down for them, allowing many to survive the journey and be detected on the ground. This observation provides compelling evidence for the reality of time dilation in our universe. Gravity's influence on time is a fascinating aspect of our universe, revealing the deep connection between space and time. This phenomenon, known as gravitational time dilation, is a key prediction of Einstein's theory of general relativity. The stronger the gravitational field, the slower time passes. On Earth, we experience this effect in subtle ways. Clocks at sea level tick slightly slower than those on mountaintops, where gravity is weaker. The difference is minuscule in our daily lives, but it becomes significant when we consider more extreme gravitational environments. Near massive objects like black holes, time slows down dramatically. If you were to observe a clock falling into a black hole, you'd see it tick more slowly as it approaches the event horizon. For the clock itself, time would appear to pass normally, but to an outside observer, it would seem to slow to a crawl. This warping of time by gravity isn't just a theoretical concept. It has practical implications for technologies we use every day. Global Positioning System satellites, for instance, must account for time dilation to provide accurate location data. Without these adjustments, GPS systems would drift by several kilometers each day, rendering them useless for navigation. Wormholes are hypothetical tunnels through space and time that could potentially create shortcuts for long journeys across the universe. Imagine the fabric of space-time as a sheet of paper. Instead of traveling across the surface, a wormhole would be like folding the paper and punching a hole through it, allowing for nearly instantaneous travel between two distant points. The concept of wormholes emerges from Einstein's theory of general relativity, which describes how gravity warps the fabric of space-time. While they remain purely theoretical, some scientists believe wormholes could exist naturally in the universe or potentially be created artificially. However, even if wormholes do exist, they present significant challenges for potential travel. They would likely be incredibly small, unstable, and collapse quickly. Some theories suggest that exotic forms of matter with negative energy density might be required to keep a wormhole open and traversable. Furthermore, the intense gravitational forces and radiation near a wormhole would likely make them extremely dangerous for any physical object attempting to pass through. Despite these obstacles, wormholes continue to captivate scientists and science fiction enthusiasts alike, representing a tantalizing possibility for faster-than-light travel and exploration of the cosmos. Space-time curvature fundamentally reshapes our understanding of gravity and orbital motion. In this framework, massive objects like stars and planets warp the fabric of space-time around them, creating a four-dimensional landscape of hills and valleys. Smaller objects, such as moons or spacecraft, follow the contours of this curved space-time as they move. Imagine a large ball placed on a stretched rubber sheet. The ball's weight creates a depression in the sheet, and smaller objects rolled nearby would naturally follow curved paths around this central mass. Similarly, planets orbit the Sun not because of a mysterious attractive force, but because they are following the path of least resistance through curved space-time. This curvature explains why objects in orbit appear to be in constant free fall. They are essentially falling towards the central body, but their sideways velocity causes them to continually miss the surface, resulting in a stable orbit. The more massive an object, the more it curves space-time, which is why larger bodies have stronger gravitational effects. Space-time curvature also accounts for phenomena like the precession of Mercury's orbit and the bending of light around massive objects, providing a more comprehensive and accurate description of gravitational interactions than classical Newtonian physics. Frame dragging is a fascinating effect predicted by Einstein's theory of general relativity. It occurs when a massive rotating object, like a planet or a black hole, twists the fabric of space-time around it. This warping of space-time causes nearby objects to be dragged along in the direction of the rotation, similar to how a spinning ball in molasses would drag the surrounding liquid with it. Scientists have measured frame dragging using several ingenious methods. One of the most notable experiments was Gravity Probe B, launched by NASA in 2004. This satellite contained 4 incredibly precise gyroscopes that could detect minute changes in their orientation caused by frame dragging as they orbited Earth. After years of data analysis, the results confirmed Einstein's predictions with remarkable accuracy. Another method used to detect frame dragging involves observing the orbits of satellites. The Italian LAIRS satellite, launched in 2012, acts as a test mass in Earth's gravitational field. By tracking its orbit with extreme precision using laser ranging, scientists can measure the subtle effects of frame dragging on its motion. Astronomers have also observed frame dragging effects in binary pulsar systems, where two dense neutron stars orbit each other. The extreme gravitational fields in these systems amplify the frame dragging effect, making it easier to detect through careful timing of the pulsar's radio emissions. These measurements not only confirm the existence of frame dragging, but also provide valuable tests of general relativity in strong gravitational fields. Black holes warp the fabric of space-time to an extraordinary degree, creating some of the most extreme environments in the universe. Their immense gravitational pull is so powerful that it distorts the very structure of reality around them. Near a black hole, space becomes severely curved, and time slows down dramatically compared to regions farther away. This warping of space-time leads to fascinating phenomena. As you approach a black hole, time dilation becomes increasingly pronounced. An outside observer would see time moving much slower for an object falling toward the black hole. This effect becomes infinite at the event horizon, the boundary beyond which nothing can escape the black hole's grasp. The extreme gravity of a black hole also affects the path of light. Light rays that pass close to a black hole can be bent or even trapped in orbit around it. This creates a phenomenon known as gravitational lensing, where the black hole acts like a cosmic magnifying glass, distorting and amplifying the light from distant objects behind it. Perhaps most intriguingly, the laws of physics as we understand them break down at the center of a black hole, in a region called the singularity. Here, the curvature of space-time becomes infinite, challenging our current theories and pushing the boundaries of our understanding of the universe. The twin paradox is a thought experiment in special relativity that explores the effects of time dilation. It involves two twins, one who stays on Earth and another who embarks on a high-speed journey through space. According to the principles of relativity, time passes more slowly for objects moving at high velocities compared to those at rest. In this scenario, the traveling twin experiences time at a slower rate due to their high-speed motion. When they return to Earth, they find that they have aged less than their Earth-bound sibling. This outcome might seem paradoxical at first glance, as each twin could claim to be the one in motion relative to the other. The resolution to this apparent paradox lies in the fact that the traveling twin undergoes acceleration and deceleration, which breaks the symmetry between the two reference frames. The Earth-bound twin remains in an inertial reference frame, while the space-faring twin does not. This difference in acceleration is key to understanding why the traveling twin truly experiences less time passage. The twin paradox reveals fundamental truths about the nature of space and time in our universe. It demonstrates that time is not absolute but relative, depending on an object's motion and gravitational influences. This concept challenges our everyday intuitions about the world and highlights the profound implications of Einstein's theory of relativity for our understanding of the cosmos. Reconciling quantum mechanics with general relativity remains one of the most significant challenges in modern physics. These two fundamental theories describe the universe at vastly different scales, yet they seem incompatible when applied to extreme conditions like black holes or the early universe. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity explains gravity and the structure of space-time at cosmic scales. The conflict arises when we try to describe gravity at the quantum level or apply quantum principles to massive objects. Scientists have proposed several approaches to bridge this gap. String theory suggests that all particles and forces are actually tiny vibrating strings in multiple dimensions. Loop quantum gravity attempts to quantize space-time itself, describing it as a network of discrete units. Other theories, like causal set theory, propose that space-time has a fundamental discrete structure at the smallest scales. Despite decades of research, a complete theory of quantum gravity remains elusive. Some physicists believe that a paradigm shift might be necessary, requiring us to rethink our fundamental understanding of space, time, and the nature of reality itself. The quest for a unified theory continues, driving innovation in theoretical physics and potentially revolutionizing our understanding of the universe. Dark matter is an invisible form of matter that doesn't interact with light or other forms of electromagnetic radiation. Scientists believe it exists because of its gravitational effects on visible matter in the universe. Observations of galaxies and galaxy clusters show that they move and behave as if they contain much more mass than we can see with our telescopes. One of the most compelling pieces of evidence for dark matter comes from studying the rotation of galaxies. Based on the visible matter alone, the outer regions of galaxies should rotate much slower than they actually do. This suggests there must be additional unseen mass providing the extra gravitational pull to keep these outer regions moving so quickly. Another clue comes from gravitational lensing, where the light from distant galaxies is bent by the gravity of massive objects between us and those galaxies. The amount of bending observed is often much greater than what visible matter alone can account for, indicating the presence of additional invisible mass. Scientists estimate that dark matter makes up about 85% of all matter in the universe. Despite its abundance, we still don't know what dark matter is made of. Numerous experiments are underway to detect dark matter particles directly, but so far, it remains one of the biggest mysteries in modern cosmology. Scientists are employing various ingenious methods to directly detect dark matter particles, despite their elusive nature. One approach involves using extremely sensitive detectors placed deep underground to shield them from cosmic rays and other interference. These detectors are designed to capture the rare interactions between dark matter particles and normal matter. Some experiments use liquid xenon or argon as the detection medium, cooling it to very low temperatures. When a dark matter particle collides with an atom in the liquid, it should produce a tiny flash of light and a few free electrons, which can be detected by sophisticated sensors. Other detectors use crystals like sodium iodide or germanium, which should produce small vibrations or temperature changes when struck by a dark matter particle. Another promising method involves searching for axions, hypothetical particles that could compose dark matter. These experiments use powerful magnets and microwave cavities to try to convert axions into detectable photons. Additionally, some scientists are exploring the use of atom interferometry, which could potentially detect the gravitational effects of dark matter on clouds of ultra-cold atoms. Despite years of searching, no conclusive direct detection of dark matter particles has been made yet. However, each new experiment and technological advancement brings us closer to potentially unveiling the nature of this mysterious substance that makes up a significant portion of our universe. Dark energy remains one of the most enigmatic phenomena in the universe. This mysterious force is believed to be responsible for the accelerating expansion of the cosmos, pushing galaxies apart at an ever-increasing rate. Unlike gravity, which pulls matter together, dark energy acts as a repulsive force on the grandest scales of the universe. The discovery of dark energy came as a shock to the scientific community in the late 1990s. Two independent teams of astronomers were studying distant supernovae, exploding stars that serve as cosmic distance markers. Their goal was to measure how the expansion of the universe had changed over time. The expectation was that the expansion would be slowing down due to the gravitational pull of all the matter in the cosmos. To their astonishment, both teams found that the expansion of the universe was actually speeding up. This acceleration could not be explained by any known form of matter or energy. To account for this unexpected observation, scientists proposed the existence of dark energy, a previously unknown component of the universe that counteracts the attractive force of gravity. Since its discovery, numerous observations have confirmed the presence of dark energy, including studies of the cosmic microwave background and the large-scale structure of the universe. However, its fundamental nature remains a profound mystery. Scientists continue to explore various theories, from the energy of the vacuum of space to modifications of Einstein's theory of gravity, in their quest to understand this elusive cosmic force that shapes the destiny of our universe. Cosmic inflation is a theory that describes a period of rapid expansion in the very early universe, occurring just a fraction of a second after the Big Bang. During this brief moment, the universe is thought to have expanded faster than the speed of light, growing from a subatomic scale to the size of a grapefruit in an unimaginably short time. This theory was proposed to solve several puzzles in cosmology, including the horizon problem and the flatness problem. The horizon problem asks why distant regions of the universe appear so similar when they shouldn't have had time to interact. Inflation solves this by suggesting these regions were once in close contact before being rapidly stretched apart. Evidence supporting cosmic inflation comes from several sources. The cosmic microwave background radiation, a faint glow left over from the early universe, shows a remarkable uniformity that aligns with inflation's predictions. Additionally, the distribution of galaxies and large-scale structures in the universe matches what we would expect if inflation occurred. Perhaps most compellingly, gravitational waves detected in the cosmic microwave background provide strong support for inflation. These ripples in spacetime, predicted by inflation theory, were observed by the BICEP-2 experiment, though later analysis showed some uncertainty in these results. Despite this, the overall body of evidence continues to support cosmic inflation as our best explanation for the early moments of the universe. The imbalance between matter and antimatter in our universe is one of the most intriguing puzzles in physics. This asymmetry, known as baryon asymmetry, is crucial for our existence. If equal amounts of matter and antimatter had been created in the early universe, they would have annihilated each other completely, leaving nothing but pure energy. Scientists believe the answer lies in the first moments after the Big Bang. During this period, the universe underwent a process called baryogenesis, where slightly more matter than antimatter was produced. This tiny imbalance, perhaps just one extra particle of matter for every 10 billion pairs of particles and antiparticles, led to the matter-dominated universe we see today. One leading explanation for this asymmetry involves a concept called charge parity violation. This phenomenon suggests that the laws of physics might have acted differently on matter and antimatter in the early universe, favoring the production of matter. Another possibility is that neutrinos, elusive particles with very little mass, played a role in creating this imbalance through a process called leptogenesis. Despite these theories, the exact mechanism behind the matter-antimatter asymmetry remains one of the biggest unsolved problems in physics. Ongoing experiments at particle accelerators and neutrino detectors around the world are working to unravel this cosmic mystery, potentially revealing fundamental truths about the nature of our universe and its origins. The cosmic censorship hypothesis addresses one of the most intriguing puzzles in our understanding of black holes and the fabric of spacetime. Proposed by physicist Roger Penrose in 1969, this concept suggests that the universe protects us from observing certain extreme phenomena that could challenge our fundamental theories of physics. At its core, the hypothesis states that singularities, points of infinite density and curvature in spacetime, are always hidden behind event horizons. These event horizons act as cosmic veils, preventing outside observers from witnessing the bizarre physics that might occur at singularities. This idea emerged as a response to solutions in general relativity that seem to allow for naked singularities, which are singularities without an event horizon to obscure them. The implications of this hypothesis are profound. If true, it would mean that the laws of physics as we know them remain valid throughout the observable universe. It would protect the predictive power of general relativity by ensuring that the extreme conditions at singularities, where our current theories break down, remain forever hidden from view. However, the cosmic censorship hypothesis remains unproven. Physicists continue to debate its validity and search for potential counterexamples. Some theories suggest that quantum effects might allow for brief glimpses of naked singularities, while others propose that the formation of such entities might be possible under specific, extreme conditions. The ongoing investigation of this hypothesis drives research in both theoretical physics and observational astronomy, pushing the boundaries of our understanding of the cosmos. The information paradox of black holes is a perplexing problem that challenges our understanding of fundamental physics. At its core, this paradox arises from the conflict between quantum mechanics and general relativity when applied to black holes. According to general relativity, anything that crosses a black hole's event horizon is lost forever, crushed into a singularity from which nothing can escape. This suggests that all information about the object's original state is destroyed. However, quantum mechanics insists that information cannot be truly lost or destroyed in the universe. The paradox deepens when we consider Hawking radiation, the theoretical process by which black holes slowly evaporate over time. As a black hole emits this radiation and gradually shrinks, it should eventually disappear completely. But if the black hole vanishes, what happens to all the information it supposedly consumed? Quantum theory demands that this information must somehow be preserved, yet no clear mechanism for its recovery has been identified. This contradiction between two fundamental theories of physics has puzzled scientists for decades. Proposed solutions range from the idea that information is encoded on the event horizon itself to more exotic concepts like information leaking out through wormholes. Despite intense research, a fully satisfactory resolution to the black hole information paradox remains elusive, making it one of the most intriguing mysteries in modern physics. The flatness problem in cosmology is a puzzling aspect of our universe that scientists have grappled with for decades. This conundrum arises from observations showing that the universe appears to be remarkably flat on large scales, far flatter than cosmological models initially predicted. One leading solution to the flatness problem comes from the theory of cosmic inflation. This theory proposes that in the earliest moments after the Big Bang, the universe underwent a brief period of exponential expansion. During this inflationary phase, the universe grew at an incredible rate, smoothing out any initial curvature and leaving behind the flat geometry we observe today. Another approach to resolving the flatness problem involves the concept of a cyclic universe. This model suggests that our universe goes through repeated cycles of expansion and contraction. In this scenario, each cycle would tend to flatten the universe, potentially explaining its current state without requiring inflation. Some scientists explore the possibility that the flatness of the universe is simply a fundamental property, perhaps arising from quantum effects or underlying physical laws we have yet to fully understand. Ongoing research in quantum gravity and other cutting-edge fields may provide new insights into this cosmic puzzle, potentially revealing novel solutions to the flatness problem that we have not yet conceived. The horizon problem is a puzzling aspect of our universe that challenges our understanding of its early history. It arises from the observation that distant regions of space, which should have never been in contact with each other, appear remarkably similar in temperature and other properties. This uniformity is seen in the cosmic microwave background radiation, the oldest light we can observe from the early universe. The issue is that light, which carries information, has not had enough time to travel between these far-apart regions since the beginning of the universe. Without some mechanism to explain this, these areas should have evolved independently and show significant differences. Yet, they do not, presenting a conundrum for cosmologists. Inflation theory offers a compelling solution to this problem. It proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. During this brief but intense phase, the universe grew in size by a factor of at least 10 raised to the power of 26 in less than a trillionth of a second. This rapid expansion would have taken regions that were once in close contact and stretched them far apart, explaining the observed uniformity across vast distances. Inflation thus provides a mechanism for the entire observable universe to have originated from a small, causally connected region, resolving the horizon problem and accounting for the remarkable consistency we see in the cosmic microwave background. The Fermi paradox, named after physicist Enrico Fermi, addresses the apparent contradiction between the high probability of extraterrestrial civilizations existing and the lack of evidence for such civilizations. Several intriguing solutions have been proposed to resolve this paradox. One proposed solution is the idea of the Great Filter. This concept suggests that there might be an insurmountable obstacle that prevents civilizations from reaching a level of technological advancement necessary for interstellar communication or travel. This filter could be a past event, such as the emergence of complex life, or a future challenge, like avoiding self-destruction through nuclear war or climate change. Another possibility is the zoo hypothesis, which posits that advanced alien civilizations are aware of us but choose not to make contact. They might be observing Earth as a sort of cosmic wildlife preserve, allowing our civilization to develop naturally without interference. This idea suggests that we might be part of a grand experiment or protected ecosystem. Some scientists propose that we might be alone in the universe, or at least in our galaxy. The rare Earth hypothesis argues that the conditions necessary for complex life to evolve are exceptionally uncommon, making Earth a unique oasis of life in a largely barren cosmos. This solution suggests that while simple life might be widespread, intelligent life capable of interstellar communication could be exceedingly rare. Life as we know it requires several fundamental elements to exist and thrive. Water is perhaps the most crucial component, serving as a universal solvent that facilitates chemical reactions necessary for life processes. Liquid water provides an environment where complex molecules can form and interact. Carbon is another essential ingredient, forming the backbone of organic compounds and enabling the creation of complex molecules like proteins and nucleic acids. These carbon-based molecules are vital for storing genetic information and carrying out cellular functions. Energy is indispensable for life, driving metabolic processes and allowing organisms to grow, reproduce, and maintain their internal structures. This energy often comes from sunlight or chemical sources, depending on the organism and its environment. Lastly, life needs a stable environment with the right temperature range and protection from harmful radiation. These conditions allow biochemical reactions to occur at appropriate rates and prevent damage to delicate cellular structures. Earth provides these conditions, making it an ideal habitat for the diverse forms of life we observe today. Extremophiles, organisms that thrive in extreme environments on Earth, have revolutionized our understanding of the potential for life beyond our planet. These remarkable creatures, found in places once thought inhospitable, have expanded our definition of habitable environments and reshaped our approach to the search for extraterrestrial life. By studying extremophiles, scientists have discovered that life can exist in conditions far more diverse than previously imagined. Some microorganisms survive in boiling hot springs, while others flourish in the frigid depths of Antarctic lakes. Certain bacteria thrive in highly acidic environments, and some organisms can withstand intense radiation levels. This diversity suggests that life might be more resilient and adaptable than we once believed, increasing the likelihood of finding it elsewhere in the universe. The existence of these hardy organisms has prompted researchers to reconsider which celestial bodies might harbor life. Moons like Europa and Enceladus, with their subsurface oceans, are now prime candidates for potential extraterrestrial habitats. Even Mars, with its harsh environment, remains a subject of interest due to the possibility of microbial life existing beneath its surface or in protected niches. Extremophiles have also influenced the development of new tools and techniques for detecting life beyond Earth. Scientists now design instruments capable of identifying biosignatures associated with these resilient organisms. expanding our ability to recognize potential signs of life in extreme extraterrestrial environments. This knowledge not only guides our search for life in the cosmos, but also helps us understand the limits and possibilities of life itself. Panspermia is the hypothesis that life exists throughout the universe and can be distributed by space dust, meteoroids, asteroids, comets, and even spacecraft. This concept suggests that life on Earth may have originated from microorganisms or chemical precursors of life present in outer space. There are several proposed mechanisms for how panspermia might occur. One possibility is that microorganisms attached to rocks could be ejected into space by the impact of large meteorites on a planet's surface. These microbe-carrying rocks could then travel through space and potentially land on other celestial bodies. Another potential avenue for panspermia involves the transfer of organic molecules or simple life forms through interstellar dust. Tiny particles containing these building blocks of life could drift through space and eventually become incorporated into newly forming planetary systems. Some scientists have also suggested that comets, which contain large amounts of water and organic compounds, could serve as vehicles for transporting life across vast cosmic distances. As comets pass through a solar system, they might deposit these materials onto planets or moons, potentially seeding them with the ingredients necessary for life to develop. Scientists employ a range of sophisticated techniques to search for biosignatures on other planets. These methods involve both remote sensing from Earth and space-based telescopes, as well as direct exploration using robotic probes and landers. One key approach is spectroscopy, which analyzes the light reflected or emitted by a planet's atmosphere. This technique can detect specific molecules that might indicate the presence of life, such as oxygen, methane, or water vapor. Scientists look for combinations of these gases that would be difficult to explain through non-biological processes. Another method involves studying the surface features of planets and moons using high-resolution imaging. This can reveal landscape patterns or color variations that might suggest biological activity. For instance, the presence of large areas of vegetation could potentially be detected through subtle changes in the way light is reflected from a planet's surface. Robotic missions to other worlds provide the most direct means of searching for biosignatures. These spacecraft can analyze soil and rock samples, search for organic compounds, and even look for microscopic fossils or current microbial life. Future missions are being planned with increasingly sophisticated instruments designed specifically to detect signs of past or present life on other planets. Life as we know it on Earth is based on carbon and water, but in vastly different environments, life could take on forms we can barely imagine. On worlds with extremely cold temperatures, like Saturn's moon Titan, organisms might use methane or ethane as a solvent instead of water. These hypothetical creatures could have cell membranes made of complex hydrocarbons, allowing them to survive in liquid methane oceans. In high-pressure environments, such as deep within gas giants like Jupiter, life could potentially exist as buoyant balloon-like organisms. These beings might float through different atmospheric layers, extracting energy and nutrients from the surrounding gases. Their bodies could be composed of strong, flexible materials capable of withstanding intense pressures and winds. On planets with extreme heat and acidity, silicon-based life forms might evolve instead of carbon-based ones. These organisms could have bodies made of silicone-like substances, allowing them to withstand temperatures that would destroy Earth-like life. They might use sulfuric acid as a solvent, thriving in conditions similar to those found on Venus. In environments bathed in intense radiation, life could develop remarkable shielding mechanisms. Organisms might incorporate heavy metals into their cellular structures or develop biological Faraday cages to protect themselves. These life forms could potentially harness radiation as an energy source, much like plants on Earth use sunlight for photosynthesis. Life on Earth likely began in the primordial oceans, around 4 billion years ago. The early Earth was a harsh environment, bombarded by meteors and bathed in intense ultraviolet radiation. Despite these challenges, the basic building blocks of life were present: water, carbon-based molecules, and energy from the sun and hydrothermal vents. One leading theory suggests that life started in these deep-sea hydrothermal vents. These underwater volcanic systems provided a protective environment rich in minerals and chemical energy. Here, simple organic molecules could have combined to form more complex structures, eventually leading to the first self-replicating molecules, the precursors to deoxyribonucleic acid. Another possibility is that life began in shallow pools on the Earth's surface. In this scenario, cycles of wetting and drying could have concentrated organic molecules, facilitating the chemical reactions necessary for life. Regardless of where it started, early life would have been simple, single-celled organisms that gradually evolved into the diverse forms we see today. This process could certainly occur elsewhere in the universe. Many of the ingredients necessary for life as we know it are common throughout the cosmos. Planets and moons with liquid water, organic molecules, and energy sources exist in our solar system and beyond. While we have not yet discovered life beyond Earth, the conditions that gave rise to life here could well exist on distant worlds, making the emergence of life elsewhere a tantalizing possibility. Comets and asteroids are more than just celestial wanderers. They may be cosmic couriers of life. These celestial bodies have likely played a crucial role in the potential spread of organic compounds and possibly even simple life forms across the vastness of space. Comets, often described as dirty snowballs, are rich in water ice and organic molecules. As they hurtle through space, they can deposit these life-giving ingredients onto planets and moons. This process, known as panspermia, suggests that the building blocks of life could be distributed throughout the universe by these icy travelers. Asteroids, while typically composed of rock and metal, can also harbor organic compounds and water in their interiors. When these objects collide with planets, they can deliver these vital materials, potentially kick-starting the chemical processes that lead to life. The impact of an asteroid or comet can also create hydrothermal systems, providing energy and a suitable environment for simple organisms to thrive. Furthermore, these cosmic impacts can eject material from one world into space, potentially carrying microorganisms to other planets or moons. This mechanism could allow life to spread not only within our solar system, but potentially between star systems over vast periods of time. While we have yet to find definitive evidence of life beyond Earth, the role of comets and asteroids in this cosmic dispersal remains a fascinating area of scientific inquiry. Preventing contamination when exploring other planets is a critical concern for space agencies worldwide. This process, known as planetary protection, involves stringent protocols and advanced technologies to ensure we don't inadvertently introduce Earth-based microorganisms to other celestial bodies or bring potentially harmful extraterrestrial materials back to our planet. Before a spacecraft leaves Earth, it undergoes extensive sterilization procedures. These include heat treatments, chemical cleaning, and assembly in ultra-clean rooms. The level of sterilization depends on the mission's target and objectives. For example, missions to Mars, where the possibility of finding life is higher, require more rigorous cleaning than those to airless bodies like asteroids. During the mission, spacecraft are designed to minimize the risk of contamination. This includes using materials that are less likely to harbor microorganisms and implementing systems that can withstand the harsh conditions of space without breaking down and potentially releasing contaminants. For sample return missions, additional precautions are taken. Collected materials are sealed in secure containers, and upon return to Earth, they are quarantined and studied in specialized facilities. These measures protect our planet from any potential biological or chemical hazards while allowing scientists to study the samples safely. Beyond Earth, several celestial bodies in our solar system show potential for harboring life. Mars, often called our planetary neighbor, has long been a prime candidate. Recent discoveries of liquid water beneath its polar ice caps and organic molecules in its soil have bolstered hopes for finding microbial life either present or past. The icy moons of Jupiter and Saturn offer intriguing possibilities. Europa, one of Jupiter's largest moons, is covered by a thick layer of ice, beneath which scientists believe lies a vast ocean of liquid water. This subsurface ocean, warmed by tidal forces, could provide an environment suitable for life. Similarly, Saturn's moon Enceladus has shown evidence of hydrothermal activity in its subsurface ocean, ejecting plumes of water vapor and organic compounds through cracks in its icy shell. Titan, the largest moon of Saturn, presents a unique case. It is the only celestial body besides Earth known to have stable bodies of liquid on its surface. However, instead of water, Titan's lakes and seas consist of liquid methane and ethane. This raises the tantalizing prospect of life forms with a biochemistry entirely different from what we know on Earth. Venus, despite its hellish surface conditions, has garnered renewed interest. Recent detections of phosphine in its upper atmosphere have led some scientists to speculate about the possibility of microbial life surviving in the more temperate cloud layers of our sister planet. While each of these locations presents significant challenges for exploration, they remain our best hopes for discovering extraterrestrial life within our cosmic backyard. Communicating with intelligent extraterrestrial life would present an unprecedented challenge for humanity. Our first attempts might involve using mathematics and physics as universal languages. We could transmit simple numerical sequences or depictions of fundamental physical constants, which any advanced civilization should recognize. Radio signals could serve as our initial medium of communication, as they travel at the speed of light and can cover vast cosmic distances. However, the time delay between transmissions and responses might span years or even centuries, depending on the location of the alien civilization. More advanced methods might include using powerful lasers to send encoded messages or even dispatching robotic probes carrying information about Earth and humanity. These probes could potentially establish direct contact if they reach an alien world. One of the biggest hurdles would be deciphering each other's languages and concepts. We might need to develop sophisticated artificial intelligence systems to analyze and interpret alien communications, gradually building a common understanding over time. This process would require patience, creativity, and open-mindedness as we encounter potentially radically different ways of thinking and perceiving the universe. A white dwarf is the remnant core of a star that has exhausted its nuclear fuel. These stellar remnants are incredibly dense, with masses comparable to our Sun compressed into a volume similar to Earth. White dwarfs form when low to medium-mass stars, like our Sun, reach the end of their lives. The process begins as a star burns through its hydrogen fuel in its core. As the hydrogen depletes, the star expands into a red giant. During this phase, the star sheds its outer layers, creating a beautiful planetary nebula. The exposed core, no longer able to sustain fusion reactions, contracts under its own gravity. This contraction is halted by electron degeneracy pressure, a quantum mechanical effect that prevents the star from collapsing further. The result is a white dwarf, a hot, dim ember of a once bright star. These stellar remnants are so dense that a teaspoon of white dwarf material would weigh several tons on Earth. White dwarfs will continue to cool and dim over billions of years, eventually becoming black dwarfs. However, the universe is not yet old enough for any white dwarfs to have reached this state, making them a testament to the ongoing evolution of stars in our cosmos. Neutron stars and pulsars are closely related cosmic objects, but they have distinct characteristics that set them apart. Neutron stars are the incredibly dense remnants of massive stars that have exploded as supernovae. These stellar corpses pack more mass than our Sun into a sphere only about 20 kilometers across, resulting in an object so dense that a teaspoon of its material would weigh billions of tons on Earth. Pulsars, on the other hand, are a specific type of neutron star. What makes them unique is their rapid rotation and powerful magnetic fields. As pulsars spin, they emit beams of electromagnetic radiation from their magnetic poles. These beams sweep across space like cosmic lighthouses, and when they pass Earth, we detect them as regular pulses of radiation, hence the name pulsar. The key difference lies in their observational properties. While all pulsars are neutron stars, not all neutron stars are pulsars. Some neutron stars rotate too slowly or have magnetic fields too weak to produce the characteristic pulsed emission. Additionally, the orientation of a neutron star relative to Earth determines whether we can detect its pulses, even if it is rapidly rotating. Pulsars also tend to slow down over time as they lose rotational energy, eventually reaching a point where they no longer emit detectable pulses. At this stage, they become more like typical neutron stars, continuing to exist as incredibly dense stellar remnants, but without the distinctive pulsing behavior that once defined them. Magnetars are a rare type of neutron star, the collapsed cores of massive stars that have exploded as supernovae. These cosmic objects are characterized by their incredibly powerful magnetic fields, which are the strongest known in the universe. To put this in perspective, a magnetar's magnetic field is about 1 quadrillion times stronger than Earth's magnetic field. This extreme magnetism is what makes magnetars so remarkable. The magnetic field is so intense that it affects the physical properties of matter in ways we can barely comprehend. It can distort the electron clouds around atoms, making chemistry as we know it impossible in its vicinity. The field is strong enough to split light into 2 separate beams and can even cause vacuum polarization, a quantum effect where the very fabric of space becomes birefringent. Magnetars also exhibit violent behavior. They frequently produce powerful bursts of gamma rays and X-rays, sometimes bright enough to be detected across the galaxy. These bursts are thought to occur when the magnetic field shifts and realigns, causing starquakes on the magnetar's surface. In some cases, these eruptions release more energy in a fraction of a second than our Sun does in hundreds of thousands of years. The extreme nature of magnetars poses many questions for scientists. How do they form such powerful magnetic fields? How long can these fields last? What can they teach us about the behavior of matter in extreme conditions? As we continue to study these enigmatic objects, we gain new insights into the most extreme physics in the universe. Binary systems containing stellar remnants follow fascinating evolutionary paths. These systems often consist of a normal star paired with a compact object like a white dwarf, neutron star, or black hole. As the normal star ages and expands, it can transfer material to its compact companion through a process called accretion. In systems with white dwarfs, this accretion can lead to nova explosions when enough hydrogen accumulates on the white dwarf's surface. In some cases, if the white dwarf gains enough mass to approach the Chandrasekhar limit, it may trigger a Type I, a supernova explosion. For systems with neutron stars or black holes, the accreted material forms a disk around the compact object. This accretion disk heats up to extreme temperatures, emitting X-rays and other high-energy radiation. These systems are often observed as X-ray binaries, providing astronomers with valuable insights into the behavior of matter under extreme conditions. Over time, the evolution of these binary systems can lead to various outcomes. The normal star might be completely consumed by its compact companion, or it could evolve into a compact object itself, forming a double compact object system. These pairs of stellar remnants are of great interest to scientists, as they can eventually merge, producing gravitational waves and potentially other observable phenomena. A Type Ia supernova is a cosmic explosion that occurs when a white dwarf star in a binary system reaches a critical mass. This happens as the white dwarf pulls matter from its companion star or collides with another white dwarf. When the white dwarf reaches about 1.4 times the mass of our Sun, it can no longer support itself against gravity. This triggers a runaway nuclear fusion reaction, causing the star to explode in a brilliant burst of light. What makes Type Ia supernovae crucial for cosmology is their consistent brightness. These explosions always release roughly the same amount of energy, making them reliable cosmic distance markers. Astronomers call them standard candles because their intrinsic brightness is known. By measuring how bright they appear from Earth, scientists can calculate their distance with remarkable accuracy. This consistency allows cosmologists to measure vast distances across the universe. By studying Type Ia supernovae in distant galaxies, scientists can determine how fast these galaxies are moving away from us. This information is vital for understanding the expansion rate of the universe and its overall structure. Perhaps most importantly, observations of distant Type Ia supernovae led to the discovery that the universe's expansion is accelerating. This unexpected finding revolutionized our understanding of the cosmos and led to the concept of dark energy, a mysterious force that counteracts gravity on the largest scales. This discovery was so significant that it earned the Nobel Prize in Physics in 2011, highlighting the immense importance of Type Ia supernovae in shaping our modern view of the universe. Stellar remnants, the dense cores left behind after stars exhaust their fuel, exert profound influences on their cosmic neighborhoods. These objects, which include white dwarfs, neutron stars, and black holes, continue to shape space long after their parent stars have faded away. White dwarfs, the most common stellar remnants, create planetary nebulae as they shed their outer layers. These glowing clouds of gas and dust enrich the interstellar medium with heavy elements, providing raw materials for future star formation. Despite their small size, white dwarfs have intense gravitational fields that can distort the orbits of nearby objects and even cause tidal disruption of planets or asteroids that venture too close. Neutron stars, the ultra-dense remnants of more massive stars, have even more dramatic effects. Their powerful magnetic fields accelerate particles to near light speed, creating jets and winds that can span vast distances. Pulsars, rotating neutron stars, sweep these beams across space like cosmic lighthouses, influencing the surrounding gas and dust. In binary systems, neutron stars can strip material from companion stars, forming accretion disks and generating X-rays that heat the surrounding space. Black holes, the most extreme stellar remnants, warp the very fabric of space-time around them. Their immense gravity can capture nearby matter, creating swirling accretion disks that emit intense radiation. Supermassive black holes at galactic centers play a crucial role in shaping entire galaxies, their gravitational influence extending far beyond their immediate vicinity. Through these various mechanisms, stellar remnants continue to be active participants in cosmic evolution, their legacy extending far beyond the lifespan of their progenitor stars. Stellar remnants offer a unique laboratory for studying extreme physics. These objects, including white dwarfs, neutron stars, and black holes, allow us to observe matter and energy in conditions far beyond what we can replicate on Earth. White dwarfs, the remnants of smaller stars, teach us about electron degeneracy pressure and how matter behaves when compressed to incredible densities. By studying their cooling rates, we gain insights into the age of our galaxy and the life cycles of stars. Neutron stars push our understanding even further. These ultra-dense objects, with masses greater than our Sun, compressed into a sphere only about 20 kilometers across, reveal the behavior of matter at nuclear densities. Their strong magnetic fields and rapid rotations produce phenomena like pulsars, which serve as precise cosmic clocks and tools for testing general relativity. Black holes, the most extreme stellar remnants, are windows into the very fabric of space-time. By observing how they affect nearby matter and light, we can test the limits of our physical theories and explore concepts like event horizons and gravitational time dilation. The study of stellar remnants continues to challenge and expand our understanding of fundamental physics. Stellar remnants play a crucial role in enriching galaxies with heavy elements, fundamentally shaping their chemical evolution. These remnants, including white dwarfs, neutron stars, and black holes, are the final stages of stellar life and death. They serve as cosmic recycling centers, dispersing newly forged elements into the surrounding space. White dwarfs, the remnants of low to medium mass stars, contribute to galactic chemistry through a process called Type Ia supernovae. When a white dwarf in a binary system accumulates enough matter from its companion, it explodes, releasing large amounts of iron and other heavy elements into the interstellar medium. These elements become the building blocks for future generations of stars and planets. Massive stars end their lives in spectacular core collapse supernovae, leaving behind neutron stars or black holes. These explosive events are responsible for creating and distributing most of the elements heavier than iron. The intense heat and pressure during a supernova trigger nuclear fusion reactions that produce elements like gold, silver, and uranium. As the star explodes, these newly formed elements are ejected into space, enriching the galactic environment. Black holes, while not directly contributing elements, play an indirect role in galactic chemical evolution. Their powerful gravitational effects can trigger star formation in nearby gas clouds, leading to the birth of new stars that will eventually produce and distribute more heavy elements. Additionally, supermassive black holes at the centers of galaxies can drive galactic winds, which redistribute chemically enriched material throughout the galaxy and even into the intergalactic medium. The Chandrasekhar limit is a crucial concept in stellar physics, named after the Indian-American astrophysicist Subramanian Chandrasekhar. This limit defines the maximum mass a white dwarf star can have while remaining stable. Specifically, it is about 1.4 times the mass of our Sun. White dwarfs are the remnants of stars like our Sun after they have exhausted their nuclear fuel. These stellar corpses are incredibly dense, with masses comparable to the Sun compressed into a volume similar to Earth. They are held up against further collapse by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same energy state. The significance of the Chandrasekhar limit lies in its role in determining the fate of stars. If a white dwarf accretes matter from a companion star or merges with another white dwarf, pushing its mass over this limit, it can no longer support itself. This triggers a runaway fusion reaction, resulting in a Type I, a supernova explosion. These supernovae are critical for cosmic chemistry, releasing heavy elements into space and serving as standard candles for measuring cosmic distances. Understanding the Chandrasekhar limit has profound implications for our knowledge of stellar evolution, supernova explosions, and the chemical enrichment of the universe. It represents a fundamental boundary in astrophysics, showcasing the interplay between quantum mechanics and gravity in shaping the cosmos. Stellar remnants, the final stages of a star's life, face different fates depending on their mass and composition. White dwarfs, the most common type of stellar remnant, gradually cool over billions of years, eventually becoming cold, dark objects known as black dwarfs. However, the universe is not yet old enough for any white dwarfs to have reached this state. Neutron stars, the ultra-dense remnants of more massive stars, can experience several possible endings. Some may slowly cool and fade, becoming increasingly difficult to detect. Others might merge with companion stars or other neutron stars, potentially triggering spectacular explosions called kilonovae. For the most massive stellar remnants, black holes, the end is less certain. They can grow by consuming nearby matter or merging with other black holes. Some theories suggest that black holes might eventually evaporate through a process called Hawking radiation, but this would take an incredibly long time for stellar mass black holes. Interestingly, some stellar remnants might not reach a quiet end at all. In certain binary systems, a white dwarf can accumulate matter from a companion star, eventually triggering a Type Ia supernova. This powerful explosion completely destroys the white dwarf, dispersing its material back into space to form new stars and planets. The cosmic web is the largest known structure in the universe, a vast network of interconnected filaments composed of dark matter and galaxies. This intricate lattice spans the observable universe, with dense galaxy clusters forming at the intersections of filaments, while vast cosmic voids occupy the spaces between. Astronomers first theorized the existence of the cosmic web in the 1980s, based on computer simulations of how matter would distribute itself under the influence of gravity over billions of years. These simulations predicted that matter would not spread evenly throughout space, but instead form a web-like structure. Observational evidence for the cosmic web began to accumulate in the 1990s and 2000s. Large-scale galaxy surveys, such as the Sloan Digital Sky Survey, mapped the three-dimensional distribution of galaxies across vast regions of space. These surveys revealed patterns consistent with the predicted web-like structure, showing galaxies clustered along filaments with voids in between. More recent observations have provided direct evidence of the cosmic web's gaseous components. Using specialized instruments and innovative techniques, astronomers have detected the faint glow of hydrogen gas in the filaments between galaxies, confirming the presence of these cosmic highways and further validating our understanding of the universe's largest-scale structure. Galaxy clusters, the largest gravitationally bound structures in the universe, form through a process of cosmic assembly that spans billions of years. These immense collections of galaxies begin their journey as slight density fluctuations in the early universe, gradually growing more massive through the relentless pull of gravity. As the universe expands and cools, these initial overdensities attract more and more matter, forming the seeds of what will become galaxy clusters. Smaller groups of galaxies and individual galaxies are drawn together, merging and coalescing into ever larger structures. This process of hierarchical formation continues over cosmic timescales, with smaller structures combining to form progressively larger ones. The evolution of galaxy clusters is marked by dramatic events and ongoing processes. Violent mergers between clusters release enormous amounts of energy, heating the intra-cluster medium to temperatures of millions of degrees. This superheated gas, primarily composed of hydrogen and helium, emits X-rays that astronomers can detect and study. Meanwhile, the galaxies within the cluster undergo transformations, with interactions and collisions reshaping their structures and altering their star formation rates. As clusters mature, they settle into a state of relative equilibrium, though they continue to grow by accreting smaller groups and individual galaxies from their surroundings. The most massive clusters can contain thousands of galaxies, vast amounts of dark matter, and enough hot gas to forge hundreds of new galaxies, if only it could cool and condense. These cosmic giants serve as laboratories for studying the interplay of gravity, dark matter, and the complex physics of galaxy evolution on the grandest of scales. Cosmic voids are vast regions of space that contain very few or no galaxies. These enormous empty areas stretch across millions of light years, forming a cosmic web structure alongside galaxy clusters and filaments. Imagine colossal bubbles of near-nothingness punctuating the universe, with the familiar stars and galaxies we observe clustered around their edges. These cosmic voids offer valuable insights into the nature of our universe. By studying their size, shape, and distribution, scientists can better understand the processes that shaped the cosmos since the Big Bang. The existence of these voids supports the theory of how gravity influences the formation and evolution of large-scale structures in the universe. Interestingly, cosmic voids are not entirely empty. They contain trace amounts of hydrogen gas and are thought to be rich in dark matter, the mysterious substance that makes up a significant portion of the universe's mass. By examining how light travels through these seemingly empty regions, researchers can probe the properties of dark energy, the enigmatic force driving the accelerating expansion of the universe. Cosmic voids also serve as natural laboratories for testing fundamental physics. Their near emptiness provides an ideal environment for studying gravity on the largest scales, potentially revealing deviations from Einstein's theory of general relativity or hinting at new fundamental forces. As we continue to map and analyze these cosmic deserts, they promise to unveil more secrets about the fabric of our universe. Cosmic filaments are vast, thread-like structures that form an intricate web across the universe, connecting galaxies, galaxy clusters, and other large-scale cosmic structures. These filaments, composed primarily of dark matter and diffuse gas, serve as cosmic highways along which matter flows and congregates. These enormous structures, spanning hundreds of millions of light-years, form the backbone of the cosmic web. They act as conduits, channeling matter from less dense regions of space toward areas of greater density. As a result, galaxies and galaxy clusters tend to form and grow along these filaments, creating a network of interconnected cosmic structures. Filaments play a crucial role in the evolution of the universe by facilitating the movement and distribution of matter. They guide the flow of gas and dark matter, influencing the formation and growth of galaxies and galaxy clusters. Over time, the gravitational pull of these filaments draws nearby matter closer, causing the filaments to become denser and more prominent. The discovery and study of these cosmic filaments have greatly enhanced our understanding of the large-scale structure of the universe. By mapping these immense threads, astronomers can trace the flow of matter and energy across cosmic distances, providing insights into the processes that have shaped our universe since its earliest moments. Dark matter plays a crucial role in shaping the large-scale structure of the universe. This mysterious substance, which does not interact with light or other forms of electromagnetic radiation, exerts a powerful gravitational influence on visible matter. In the early universe, dark matter formed vast networks of filaments and clumps, creating a cosmic web that served as a framework for the formation of galaxies and galaxy clusters. Ordinary matter was drawn into these dark matter structures, pooling in dense regions where stars and galaxies could form. The gravitational pull of dark matter continues to influence cosmic structure today. It acts as a scaffold, holding galaxy clusters together and guiding their movements through space. Without dark matter, the universe we observe would look dramatically different. Galaxies would have difficulty forming and maintaining their spiral shapes, and the largest structures in the cosmos, such as superclusters of galaxies, might not exist at all. By studying the distribution of dark matter through its gravitational effects, scientists can map the invisible cosmic web and better understand how the universe evolved over billions of years. This knowledge helps explain the current arrangement of galaxies and provides insights into the future development of cosmic structures. Astronomers employ a variety of sophisticated techniques to map the large-scale structure of the universe. One primary method involves conducting extensive galaxy surveys, where they systematically observe and catalog millions of galaxies across vast regions of space. These surveys use powerful telescopes to capture light from distant galaxies, allowing astronomers to determine their positions and distances from Earth. Spectroscopy plays a crucial role in these mapping efforts. By analyzing the light from galaxies, astronomers can measure their redshifts, which indicate how fast the galaxies are moving away from us due to the expansion of the universe. This information helps determine the galaxies' distances and their three-dimensional positions in space. Another important tool is weak gravitational lensing. This technique detects subtle distortions in the shapes of distant galaxies caused by the gravitational effects of intervening matter. By studying these distortions, astronomers can map the distribution of both visible and dark matter throughout the cosmos. Computer simulations and advanced data analysis techniques are then used to process this vast amount of information. These tools help astronomers identify patterns and structures in the galaxy distribution, revealing a cosmic web of filaments, clusters, and voids that stretch across billions of light-years. This comprehensive mapping of the universe's large-scale structure provides crucial insights into its formation, evolution, and the fundamental laws that govern our cosmos. Baryon acoustic oscillation is a remarkable phenomenon that has left its imprint on the large-scale structure of the universe. It originated in the early cosmos, about 380,000 years after the Big Bang, when the universe was a hot, dense plasma of particles and radiation. In this primordial soup, sound waves propagated through the plasma, creating areas of compression and rarefaction. These sound waves were caused by the interplay between gravity pulling matter together and radiation pressure pushing it apart. As the universe expanded and cooled, these sound waves became frozen in place, leaving a characteristic pattern in the distribution of matter. This pattern manifests as a slight preference for galaxies to be separated by a specific distance, roughly 500 million light-years apart in the present-day universe. This separation corresponds to the distance sound waves could travel before the universe became neutral and transparent, a moment known as recombination. Baryon acoustic oscillation serves as a standard ruler for cosmologists, allowing them to measure cosmic distances and the expansion rate of the universe. By studying this phenomenon, scientists can probe the nature of dark energy and gain insights into the fundamental properties of our cosmos, making it a powerful tool in our quest to understand the universe's structure and evolution. The expansion of the universe profoundly shapes cosmic structures across vast timescales. As space itself stretches, galaxies and galaxy clusters grow more distant from one another. This ongoing expansion influences the formation and evolution of cosmic structures in several key ways. On the largest scales, the expansion of the universe counteracts the pull of gravity. While gravity works to draw matter together, cosmic expansion acts as an opposing force, pulling objects apart. This interplay between gravity and expansion has shaped the growth of cosmic structures since the early universe. In the distant past, when the universe was more compact, gravity played a dominant role. It allowed matter to clump together, forming the first stars and galaxies. However, as the universe has expanded, the influence of gravity has weakened over larger distances. This has led to the formation of cosmic voids, enormous regions of space with few galaxies, surrounded by filaments and clusters where galaxies are more concentrated. Looking to the far future, cosmic expansion will continue to affect structures on the grandest scales. Galaxy clusters will become increasingly isolated as the space between them grows. Eventually, distant galaxies will recede so rapidly that their light will no longer reach us, fundamentally altering our view of the cosmos and redefining the observable universe. The distribution of galaxies across the cosmos serves as a cosmic map, revealing crucial information about the early universe. By studying how galaxies are spread out, astronomers can trace the echoes of primordial fluctuations that occurred just moments after the Big Bang. These ancient ripples in space-time grew over billions of years, eventually giving rise to the large-scale structure we observe today. One key insight from galaxy distribution is the presence of cosmic web structures. Vast filaments of galaxies stretch across space, interspersed with immense voids. This pattern closely matches theoretical predictions based on the behavior of dark matter in the early universe, providing strong support for our current cosmological models. Furthermore, the clustering of galaxies at different distances allows scientists to measure how the universe has expanded over time. By comparing the observed distribution to computer simulations, researchers can refine their understanding of dark energy, the mysterious force driving cosmic acceleration. This information helps constrain theories about the nature and evolution of the universe. The distribution of galaxies also reveals the influence of gravity over cosmic timescales. Areas with higher concentrations of galaxies indicate regions where gravity has pulled matter together more strongly, reflecting the initial density variations present in the infant universe. These observations provide valuable data for testing theories of galaxy formation and the role of dark matter in shaping cosmic structure. The cosmic web, that vast network of galaxies, galaxy clusters, and filaments stretching across the universe, is not static. Over immense timescales, it will undergo significant changes. As the universe continues to expand at an accelerating rate due to dark energy, the cosmic web will be stretched and thinned out, Galaxies and galaxy clusters that are not gravitationally bound to each other will drift farther apart, causing the voids between filaments to grow larger. Within galaxy clusters, gravitational forces will continue to pull galaxies closer together. These clusters will become more compact and isolated as they separate from other clusters. The filaments connecting these clusters will become increasingly tenuous, eventually breaking apart in many places. In the very distant future, perhaps hundreds of billions of years from now, the cosmic web as we know it may cease to exist in its current form. Most galaxies outside our local group will have receded beyond our cosmic horizon, becoming forever unobservable. The universe visible to any observer will appear increasingly empty, with only their local galaxy cluster remaining as a significant structure. This evolution of the cosmic web reflects the ongoing battle between gravity, which tries to pull matter together, and dark energy, which drives the expansion of space itself. Ultimately, dark energy is expected to dominate, fundamentally altering the large-scale structure of the universe and the cosmic landscape we observe today. The solar wind is a continuous stream of charged particles, primarily electrons and protons, that flows outward from the Sun into space. This relentless gush of particles originates in the Sun's hot outer atmosphere, known as the corona, where temperatures soar to millions of degrees. The intense heat causes the Sun's gravity to lose its grip on these particles, allowing them to escape into the solar system at speeds of hundreds of kilometers per second. As this torrent of particles races through space, it carries with it the Sun's magnetic field, creating a vast bubble called the heliosphere that extends far beyond the orbit of Pluto. The solar wind is not uniform. It varies in speed and density, sometimes flowing gently and other times erupting in violent gusts during solar storms. When the solar wind reaches Earth, our planet's magnetic field acts as a shield, deflecting most of the charged particles around us. This interaction creates a teardrop-shaped protective bubble called the magnetosphere. However, some particles do penetrate this shield, particularly near the poles where the magnetic field is weaker. These particles can trigger spectacular displays of light in the upper atmosphere, known as auroras or the northern and southern lights. The effects of the solar wind on Earth extend beyond these celestial light shows. During intense solar storms, the influx of charged particles can disrupt satellite communications, interfere with power grids, and even pose radiation risks to astronauts in space. The solar wind also plays a role in shaping the tails of comets and influences the atmospheres of other planets in our solar system, reminding us of the Sun's far-reaching influence throughout our cosmic neighborhood. Solar flares and coronal mass ejections are powerful eruptions from the Sun that can have significant effects on Earth. These explosive events release immense amounts of energy and charged particles into space, occasionally directed towards our planet. When a solar flare occurs, it emits a burst of electromagnetic radiation across the spectrum, including X-rays and ultraviolet light. This radiation travels at the speed of light, reaching Earth in about 8 minutes. It can cause disruptions to radio communications and increase the ionization of the upper atmosphere, potentially affecting satellite operations and GPS accuracy. Coronal mass ejections, often associated with solar flares, are massive clouds of magnetized plasma hurled into space. These can take anywhere from hours to days to reach Earth. When they arrive, they interact with our planet's magnetic field, causing geomagnetic storms. These storms can induce electrical currents in power grids, potentially leading to widespread blackouts. They also compress Earth's magnetic field, allowing more solar particles to enter the atmosphere near the poles. One of the most visible and harmless effects of these solar events is the creation of auroras, the beautiful displays of light seen in high-latitude regions. However, the same particles that create these light shows can also pose risks to astronauts in space and even to passengers on high-altitude polar flights, exposing them to increased levels of radiation. The magnetosphere is Earth's protective magnetic bubble, a vast region of space surrounding our planet that shields us from harmful cosmic radiation and solar wind. This invisible shield is generated by Earth's molten iron core, which acts like a giant electromagnet, creating a powerful magnetic field that extends tens of thousands of kilometers into space. As the solar wind, a stream of charged particles from the Sun, approaches Earth, it encounters the magnetosphere. This interaction causes the magnetosphere to compress on the side facing the Sun and stretch out into a long tail on the opposite side, resembling a teardrop shape. The magnetosphere deflects most of the incoming solar particles, preventing them from directly impacting our planet. The magnetosphere plays a crucial role in protecting life on Earth from the potentially damaging effects of solar and cosmic radiation. It acts as a barrier, redirecting high-energy particles away from the planet's surface and atmosphere. Without this protective shield, Earth's atmosphere could be slowly stripped away by the solar wind, and the surface would be bombarded by harmful radiation, making life as we know it impossible. In addition to its protective function, the magnetosphere is responsible for creating spectacular natural phenomena such as the auroras, also known as the northern and southern lights. These dazzling light displays occur when some solar particles manage to enter the magnetosphere and interact with atoms in the upper atmosphere, creating colorful curtains of light that dance across the polar skies. Geomagnetic storms are powerful disturbances in Earth's magnetic field triggered by intense solar activity. These storms begin when the Sun ejects a massive burst of charged particles and magnetic energy, known as a coronal mass ejection. As this solar material hurtles through space and reaches our planet, it interacts with Earth's magnetic field, causing it to fluctuate and distort. The impact of these solar particles compresses Earth's magnetic field on the day side and stretches it on the night side, much like a rubber band being pulled and twisted. This distortion allows some of the charged particles to enter Earth's upper atmosphere near the poles, creating the dazzling light displays we know as auroras. While auroras are a beautiful consequence, geomagnetic storms can have more serious effects. They can disrupt satellite communications, interfere with GPS signals, and even cause widespread power outages. In extreme cases, these storms can induce electrical currents in power grids and pipelines, potentially damaging critical infrastructure. Geomagnetic storms also pose risks to astronauts and high-altitude aircraft, as the increased radiation can be harmful to human health. Scientists closely monitor solar activity to predict these events and mitigate their potential impacts on our technology-dependent society. Cosmic rays are high-energy particles that originate from sources beyond our solar system. These particles, primarily protons and atomic nuclei, travel at nearly the speed of light and carry enormous amounts of energy. They come from various cosmic sources, including supernovas, active galactic nuclei, and possibly even from the mysterious depths of intergalactic space. As cosmic rays approach Earth, they encounter our planet's magnetic field and atmosphere. The magnetic field acts as a shield, deflecting many of these particles away from Earth. However, some cosmic rays manage to penetrate this barrier and enter our atmosphere. When they do, they collide with atoms and molecules in the air, creating a cascade of secondary particles. This collision process, known as an air shower, produces a variety of particles including muons, electrons, positrons, and pions. These secondary particles continue to interact with the atmosphere, creating more particles and losing energy as they descend. By the time they reach the Earth's surface, most of the original cosmic ray energy has been dissipated. Interestingly, cosmic rays play a role in the formation of carbon-14, a radioactive isotope used in carbon dating. They also contribute to the natural background radiation we experience on Earth and can occasionally cause minor disruptions to electronic systems, especially at high altitudes. Scientists study cosmic rays to learn about the universe's most energetic phenomena and to better understand particle physics. Space weather, the dynamic conditions in space influenced by solar activity, has significant impacts on human technology and space exploration. Solar flares and coronal mass ejections from the Sun release enormous amounts of energy and charge particles into space, creating a complex environment that interacts with Earth's magnetic field and atmosphere. These solar events can disrupt satellite communications, interfere with GPS signals, and even cause power grid failures on Earth. During intense solar storms, satellites may experience malfunctions or reduced lifespans due to increased radiation exposure. This poses challenges for our modern technological infrastructure, which relies heavily on space-based systems for communication, navigation, and weather forecasting. For space exploration, space weather presents additional risks. Astronauts venturing beyond Earth's protective magnetosphere face increased exposure to harmful radiation, which can lead to health issues and limit the duration of space missions. Space vehicles and equipment must be designed to withstand the harsh radiation environment and potential impacts from high-energy particles. Understanding and predicting space weather is crucial for safeguarding our technology and ensuring the safety of astronauts. Scientists and space agencies continuously monitor solar activity and develop advanced forecasting models to anticipate and mitigate the effects of space weather on our increasingly space-dependent society and future exploration endeavors. The solar cycle is a periodic fluctuation in the Sun's activity that occurs roughly every 11 years. During this cycle, the Sun's magnetic field completely flips, with the north and south magnetic poles switching places. This process drives changes in solar activity, including the frequency and intensity of solar flares, coronal mass ejections, and sunspots. At the peak of the solar cycle, known as solar maximum, the Sun becomes more active and volatile. Solar flares erupt more frequently, sending bursts of radiation into space. Coronal mass ejections, massive clouds of magnetized plasma, are hurled from the Sun's surface at incredible speeds. These events can have significant impacts on Earth and near-Earth space, collectively known as space weather. Space weather affects various technological systems both in orbit and on the ground. During periods of intense solar activity, satellites can experience disruptions or damage, potentially affecting communications, navigation, and weather forecasting. On Earth, geomagnetic storms induced by solar events can interfere with power grids, sometimes causing widespread blackouts. They can also create stunning auroras visible at lower latitudes than usual. Understanding the solar cycle and its effects on space weather is crucial for protecting our technology-dependent society. Scientists and space agencies closely monitor solar activity to predict potential impacts and take preventive measures to safeguard critical infrastructure and space-based assets. Scientists predict and monitor space weather events through a combination of advanced technology and comprehensive observational networks. Solar observatories, both on Earth and in space, constantly watch the Sun for signs of increased activity. These observatories use specialized instruments to detect solar flares, coronal mass ejections, and changes in the solar wind. Satellites positioned at strategic points between the Earth and the Sun act as early warning systems. The Solar and Heliospheric Observatory, located about 1 million miles from Earth, provides crucial data on solar activity. These satellites measure particle emissions, magnetic field fluctuations, and solar wind speed, allowing scientists to forecast potential impacts on Earth. Ground-based magnetometers and ionosondes monitor changes in Earth's magnetic field and ionosphere, respectively. This data helps scientists understand how solar activity affects our planet's environment. Additionally, computer models play a vital role in space weather prediction. These models use current solar observations to simulate how solar events might evolve and interact with Earth's magnetosphere. The combined data from all these sources allows space weather forecasters to issue alerts and warnings. These predictions help protect sensitive technologies, such as power grids, communication systems, and satellites, from the potentially harmful effects of space weather events. As our understanding of solar-terrestrial interactions grows, so does our ability to predict and mitigate the impacts of space weather on our increasingly technology-dependent society. Space weather, driven by the sun's activity, can produce remarkable and sometimes devastating effects on Earth and our technology. One of the most extreme events occurred in 1859, known as the Carrington event. This powerful solar storm caused auroras visible as far south as the Caribbean and disrupted telegraph systems worldwide. Operators reported sparks flying from their equipment, and some telegraph lines continued to send and receive messages even after being disconnected from their power sources. Another significant event took place in 1989 when a geomagnetic storm caused a massive blackout in Quebec, Canada. The storm induced electrical currents in power lines, overloading the grid and leaving millions without power for hours. This event highlighted the vulnerability of our modern infrastructure to space weather. In 2003, the Halloween solar storms battered Earth with a series of powerful solar flares and coronal mass ejections. These storms damaged satellites, caused radio blackouts, and forced airlines to reroute flights away from polar regions due to increased radiation exposure risks. More recently, in July 2012, Earth narrowly missed a potentially catastrophic solar storm. Had it occurred just 1 week earlier, it would have struck our planet, potentially causing widespread power outages and trillions of dollars in damage. These events remind us of the immense power of our sun and the importance of monitoring and preparing for extreme space weather. Climate change on Earth and space weather phenomena are intricately connected, with each influencing the other in complex ways. As our planet continues to warm, these interactions are likely to become more pronounced and potentially more disruptive. One significant area of concern is the impact of climate change on our upper atmosphere. As greenhouse gases accumulate in the lower atmosphere, they actually cause cooling in the upper layers, including the ionosphere. This cooling leads to contraction of the upper atmosphere, potentially altering how it interacts with incoming solar radiation and charged particles from space. These changes in the upper atmosphere could affect how space weather events, such as solar storms, impact our planet. For instance, a contracted ionosphere might be less effective at shielding us from harmful solar radiation. Additionally, changes in the density and composition of the upper atmosphere could alter the trajectories of satellites and space debris, potentially increasing the risk of collisions. Conversely, increased solar activity and space weather events could exacerbate some effects of climate change. Solar storms can cause geomagnetic disturbances that interfere with power grids and communication systems. As our society becomes increasingly reliant on technology, and as climate change puts additional stress on our infrastructure, these disruptions could become more frequent and severe.